Hello there and welcome to Science for Sleep, where we take very large questions, move through them slowly, and hopefully learn something interesting without giving your brain any reason to stay awake until 3 a.m. thinking about supermassive black holes. Tonight we're going somewhere very far away, not just to another planet, another star, or even another nearby galaxy. We're heading billions of light years into the universe to meet something so enormous that the galaxy responsible for creating it looks almost insignificant by comparison. It's called Porphyrion. And before we go any further, there is one useful distinction to make. Porphyrion is sometimes described casually as an enormous radio galaxy, but the extraordinary measurement that made it famous does not describe the diameter of the galaxy itself. The galaxy is the home of the supermassive black hole responsible for Porphyrion. What stretches across roughly 23 million light-years is the gigantic pair of radio jets, extending away from that galaxy in opposite directions. 23 million light-years. That's one of those numbers that sounds impressive before quietly becoming meaningless, because the human brain was not designed to picture distances like that. We are fairly good at imagining the distance to the kitchen. We can manage another city. With a little effort, perhaps another country. Once someone starts talking about millions of light years, however, our mental measuring tape tends to roll itself up and go home. So tonight we'll give it some help. Porphyrion is the largest known black hole jet system discovered so far, a structure produced by a supermassive black hole in a galaxy whose light has been travelling toward us for billions of years. From its central source, 2 enormous streams of energetic material reached outward through intergalactic space, together spanning around 7 megaparsecs, or about 23 million light-years from end to end. Even in astronomy, where almost everything appears to have been designed without much concern for sensible dimensions, that is unusually large. The Milky Way, depending on exactly what part of it you choose to measure, is roughly 100,000 light-years across when we're talking about its familiar stellar disk. Porphyrion's jets extend across a distance that could accommodate well over 100 Milky Way-sized galaxies placed side by side. And unlike a chain of galaxies, this structure is connected to the activity of a single central engine. One supermassive black hole feeding on material and producing jets that remained organised over an almost ridiculous distance. So, before we begin following those jets outward, let me ask you something much closer to home. Where are you listening from tonight? Maybe you're in bed with the room already dark. Maybe you're on a sofa wondering whether you're actually going to finish this video, or wake up tomorrow having mysteriously missed everything after the first 10 minutes. Perhaps you're listening from a city where the streets are still active outside, or somewhere quiet enough that the loudest thing in the room is the occasional complaint from a radiator. And what does the sky look like where you are? Maybe you can see stars. Maybe you can see 3 stars and a suspiciously bright aircraft. Or maybe the clouds have once again decided that astronomy is none of your business. Wherever you happen to be, there is something slightly strange about the fact that we can sit in an ordinary room on Earth and talk about a structure 23 million light-years long. Nothing in everyday life really prepares us for that. A light-year, despite the name, is a distance rather than a length of time. It is the distance light travels through vacuum in 1 year. Light moves at about 300,000 kilometers every second, fast enough to travel around Earth more than 7 times in a single second. Give it an entire year, and it covers roughly 9.46 trillion kilometers. Now imagine 23 million of those light-years placed end to end. Actually, don't try too hard. This is science for sleep, not science for creating a mild existential crisis before bed. The important point is simply that Porphyrion is large on a scale where our ordinary comparisons become increasingly unhelpful. And perhaps even more interesting than its size is the fact that astronomers weren't expecting black hole jets to become this large at all. Before systems such as Porphyrion were identified, scientists already knew that some galaxies could produce enormous radio jets, stretching millions of light-years. These objects are often called giant radio galaxies. Their central supermassive black holes can launch narrow streams of plasma in opposite directions and those streams can travel far beyond the visible galaxy itself. But there seem to be practical limits. Jets have to move through an environment. They encounter gas, they interact with magnetic fields, they expand, they lose energy, they can become unstable, bend, weaken, or break apart. Producing a jet is difficult enough. Keeping one coherent across millions of light years is considerably more demanding. Porphyrion managed it on a scale that surprised researchers. Its discovery was reported in 2024 by an international team led by astronomer Martin Oy. The structure appeared in radio observations made using LOFAR, the low-frequency array, a network of radio antennas spread across Europe. LOFAR does not look at the universe the way your eyes do. Our eyes detect visible light, which is a tiny section of the electromagnetic spectrum. Radio telescopes detect much longer wavelengths. And that matters because many enormous structures in the universe are not especially impressive in ordinary visible images. A galaxy might look like a distant faint smudge, while radio observations reveal huge lobes and jets extending far beyond it. In other words, if you looked toward Porphyrion using only ordinary visible light, you would not see a gigantic glowing object stretching 23 million light-years across the sky. The real spectacle appears at radio wavelengths, and that gives Porphyrion a slightly unfair advantage in the hide-and-seek department. Something can be one of the largest structures ever produced by a galaxy and still remain completely invisible to human eyes. Astronomers have known about radio galaxies for decades, but modern low-frequency radio surveys are allowing them to search huge regions of the sky with sensitivity that earlier generations simply did not have. When researchers examine those maps, they sometimes find long patches of radio emission sitting on opposite sides of a much smaller galaxy. The natural question is whether those separated patches are actually connected. Imagine seeing two enormous clouds hundreds of kilometers apart and discovering that both came from the same garden sprinkler. The scale difference would be rather alarming. With Porphyrion, the central galaxy contains the supermassive black hole responsible for launching the jets. Material near a feeding black hole can form an accretion disk, a rapidly moving region of gas and plasma heated as matter falls inward. Magnetic fields around this environment can become extremely strong and organized. Under suitable conditions, some material and electromagnetic energy are directed away from the central region in narrow beams moving at tremendous speeds. And here we meet one of the first misunderstandings people often have about black holes. Black holes are famous for pulling things inward. So hearing that a black hole is associated with two enormous jets shooting material outward can sound slightly contradictory. It feels a bit like discovering that your vacuum cleaner has been firing dust through the roof while you weren't looking. But the material in these jets does not come from inside the event horizon. Once something has crossed that boundary, it cannot simply turn around and leave. The jets are created by processes occurring in the intensely energetic region around the black hole, wherein falling matter, rotation, and magnetic fields interact. A feeding supermassive black hole can therefore become one of the brightest and most energetic engines in the universe. The black hole itself remains black. Everything happening around it is another matter. Matter in the accretion flow can heat to extreme temperatures. Radiation can pour outward. Magnetic fields can channel particles away from the central region. Jets can emerge from opposite sides, often aligned with the rotation axis of the black hole and its surrounding disk. Most of these jets do not become Porphyrion. That's worth remembering. There are many active galaxies in the universe. Plenty of them produce jets. Some jets remain confined close to their galaxies. Some extend hundreds of thousands of light years. Others reach several million. Then there is Porphyrion, continuing outward until ordinary words like large, huge, enormous, and gigantic begin competing for the same job. Its name fits rather well. Porphyrion was a giant from Greek mythology, one of the gigantes who challenged the Olympian gods. Astronomers have a long tradition of giving extraordinary cosmic objects names drawn from mythology, and this particular name is difficult to argue with. Calling it Kevin would probably have changed the mood. The mythological Porphyrion was a giant. The astronomical Porphyrion is a pair of jets so long that light itself would need about 23 million years to travel from one extreme end of the entire structure to the other. Think about that carefully. A beam of light beginning its journey at one outer edge and travelling directly along the system toward the other edge would still be travelling millions of years later. Entire species can appear and disappear during timescales like that. Continents move, mountain ranges rise and erode. On Earth, 23 million years ago, we would have been living during the Miocene epoch. Our modern human species was nowhere around. Yet that amount of time corresponds merely to the crossing time for light travelling from one side of Porphyrion's full extent to the other, and the system itself is much farther away. The host galaxy is around 7.5 billion light-years from us, meaning the light and radio emission astronomers detect today began travelling toward Earth billions of years before Earth looked anything like it does now. There were no humans waiting here to receive it. There were no telescopes. There wasn't even a sun when the earliest history of this system was unfolding in the form we are now observing. By studying distant objects, astronomy allows us to look backward in time because light takes time to travel. When we see the moon, we see it roughly 1.3 seconds in the past. Sunlight takes a little over 8 minutes to reach Earth, so the sun we see is the sun from about 8 minutes ago. Nearby stars appear as they were years or decades ago. Distant galaxies appear as they were millions or billions of years ago. Porphyrion gives us information about an era when the universe was less than half its present age. The universe today is around 13.8 billion years old. The observations place the system at a time when the cosmos was roughly 6.3 billion years old. That creates an important part of the mystery. The early universe was different from the one surrounding us now. Matter was generally packed more closely together because cosmic expansion had not yet carried galaxies and large-scale structures as far apart. The environment through which Porphyrion's jets had to travel was therefore not necessarily the easiest place to build something 23 million light-years long. Yet there it is. Or, more accurately, there it was. What we are seeing is ancient information. Porphyrion may have changed dramatically during the billions of years that its signal has been travelling to us. The active black hole could have become quiet, the jets could have faded, the host galaxy itself could have evolved or interacted with other galaxies. There is no way for us to look across that distance and see what Porphyrion is doing at this exact moment. We have received an old message, and radio astronomy is allowing us to read it. That idea becomes useful when thinking about the universe as a whole. Looking far away does not simply show us another place, it also shows us another time. A telescope capable of seeing deep into space becomes, in a practical sense, a machine for studying history. No one is travelling backward. No complicated time machine is required. You simply wait for old light to arrive. Astronomers have become quite good at this, although the waiting period is admittedly easier when the light started travelling several billion years before the astronomers were born. Porphyrion became especially interesting because its jets are not merely large compared with galaxies. They approach scales associated with the cosmic web itself. The cosmic web is the enormous arrangement of matter throughout the universe. Galaxies are not distributed randomly like crumbs dropped evenly across a floor. Gravity has organised matter into clusters, filaments, walls, and vast relatively empty regions called voids. On smaller scales, gravity gathers matter into galaxies. On much larger scales, galaxies themselves gather into structures. The result is something that looks, in computer simulations and large surveys, rather like a web. Porphyrion's jets extend far enough that they may reach across a meaningful fraction of these enormous environments. This raises questions that go beyond simply asking how a jet became so long. What happens when a black hole sends energy, particles and magnetic fields millions of light years away from its own galaxy? Could enormous jets influence gas that might later become part of other galaxies? Could they help spread magnetic fields through intergalactic space? How common were systems like this in the early universe? And perhaps the most uncomfortable question for astronomers: if Porphyrion was hiding in radio survey data until recently, how many more are still out there? That last possibility is especially interesting. Porphyrion might be a freak. It could represent an unusually lucky combination of a powerful black hole, a long period of activity, a favourable environment, and jets that remained stable for far longer than expected. Or it could be telling us that our picture of giant radio systems has been incomplete. Sometimes astronomy changes because someone builds a new theory. Sometimes it changes because someone looks with a better instrument and discovers that the universe apparently forgot to read the previous theory. LOFAR has been particularly useful for finding giant radio structures because older populations of energetic electrons can continue producing low-frequency radio emission, even when other signs of activity have weakened. Features that might be difficult to recognize at other wavelengths can stand out in detailed radio maps. That means the sky can contain structures much larger than the galaxies visible in ordinary images. You could look at a photograph of a distant galaxy and think you've seen the object. Then a radio telescope effectively says, "Not quite. There's another several million light years." Porphyrion takes that surprise to an extreme. At its center is a galaxy. Inside that galaxy is a supermassive black hole. Around that black hole, matter supplied the conditions for an active galactic nucleus. From the central region, jets travelled in opposite directions. Those jets carried energy outward through intergalactic space. They produced radio emission detectable billions of years later by instruments on a small planet orbiting an ordinary star. And now you're listening to a sleepy science video about it, which is probably not the outcome the black hole had in mind. If you're enjoying the journey so far, you can give the video a like and subscribe to Science for Sleep. It helps more people find these long, quiet explorations, particularly those who enjoy learning something before sleep, or simply need an excuse to hear the phrase supermassive black hole spoken in a calm voice. And if you're already beginning to feel sleepy, that's perfectly fine. There will be no test on megaparsecs in the morning. You don't need to memorize the numbers. You don't need to keep track of every telescope or every physical process. The useful thing for now is to hold on to the basic picture. Somewhere billions of light years away, astronomers found a galaxy whose central black hole produced 2 radio jets extending across roughly 23 million light years. That one system forces us to think about several different scales at once. There is the black hole itself, concentrated into a region tiny compared with the structure it influences. There is the host galaxy, containing billions of stars but appearing small beside the jets. There are the jets, carrying energy across millions of light years, and around all of it lies the cosmic web, the larger environment connecting galaxies across the universe. The surprising part is not simply that all these things exist, it's that they interact. A black hole in the centre of one galaxy can affect space far beyond the galaxy's visible edge. Something extremely compact can influence something extremely large. And that is where Porphyrion becomes more interesting than a record in an astronomy book. Records are temporary. The largest known jet system today may eventually become the second largest, then the third, and perhaps one day an astronomer will find something so enormous that Porphyrion suddenly seems almost modest. Science tends to do that to record holders. The deeper question is how a system like this works at all. The galaxy at the centre of Porphyrion is where this enormous structure begins, but if we could somehow travel there and look at the galaxy with ordinary human eyes, we would probably be disappointed. There would be no obvious pair of glowing beams stretching millions of light years across space. No enormous neon arrows pointing outward from the black hole. No convenient sign saying, "Largest known black hole jet system this way." Much of what makes Porphyrion extraordinary is visible not in the narrow range of light our eyes can detect, but at radio wavelengths. And that brings us to a type of object that sounds slightly misleading when you first hear its name. A radio galaxy. The name makes it sound as though the galaxy is broadcasting something. Perhaps weather reports, perhaps music, perhaps a very long program about supermassive black holes, that nobody has managed to switch off for several 100 million years. But radio galaxies are not radio stations in the ordinary sense. The radio waves we detect from them carry no deliberate message. They are produced naturally by extremely energetic particles moving through magnetic fields, often in structures that extend far beyond the stars of the galaxy itself. At visible wavelengths, a radio galaxy may look surprisingly normal. It might resemble an ordinary elliptical galaxy, containing billions or even trillions of stars. There may be gas and dust. There may be old stellar populations filling a broad, smooth glow. If the galaxy is distant enough, it may look like little more than a faint patch of light. Then astronomers point a radio telescope at the same region. And suddenly, the object gets much bigger. A compact galaxy that appears modest in visible light may be sitting between two enormous clouds of radio emission. Thin jets may connect the centre to those clouds. Bright regions can appear where the jets interact strongly with their surroundings. The full radio structure can extend hundreds of thousands or millions of light years beyond the stars. In the most extreme cases, the visible galaxy is almost like the small knot in the middle of a very large bow tie. Porphyrion takes that arrangement to an absurd scale. To understand how it happens, we need to begin with the centre of the galaxy. Most large galaxies appear to contain a supermassive black hole in their central region. The Milky Way has one too, called Sagittarius, a star, with a mass of roughly 4 million suns. That sounds quite substantial, and it is. You would certainly notice 4 million suns if someone left them in your driveway. But supermassive black holes come in a wide range of masses, and some contain hundreds of millions or billions of times the mass of the Sun. Simply having a supermassive black hole, however, does not make a galaxy a powerful radio galaxy. The important question is what that black hole is doing. Our own central black hole is currently fairly quiet. There is material around it, and occasional activity occurs, but Sagittarius A star is not presently consuming enough matter to produce the kind of spectacular large-scale activity seen in powerful active galaxies. In other galaxies, conditions can be very different. Gas, dust, and other material may find their way toward the central black hole. It does not usually fall straight in like water disappearing down a drain. Matter has motion. It has angular momentum. Instead of simply dropping directly toward the event horizon, much of it forms a rotating structure around the black hole called an accretion disk. Closer to the black hole, conditions become extreme. Material moves very quickly. Friction and other processes heat the gas. Magnetic fields become important. Large amounts of gravitational energy can be converted into radiation and motion. The central region can become extraordinarily bright. When a supermassive black hole is actively feeding in this way, astronomers call the energetic central region an active galactic nucleus, usually shortened to AGN. The black hole itself is still black. That point is worth keeping clear because illustrations can sometimes make it seem as though black holes are glowing balls. They aren't. The event horizon does not shine like the surface of a star. The spectacular radiation comes from matter and energetic processes outside it. So when astronomers talk about an active black hole producing huge amounts of energy, they're usually talking about the environment around the black hole, rather than something escaping from inside it. Nothing crosses the event horizon, changes its mind, checks the return policy, and comes back out as a jet. The jets begin outside that boundary. Exactly how black hole jets are launched is an active area of astrophysics, and the details involve some fairly serious plasma physics, magnetic fields, relativity, and equations that are probably best not invited onto the pillow tonight. The broad idea is manageable. A rotating black hole, a surrounding accretion flow, and powerful magnetic fields can create conditions that channel energy and plasma away from the central region. Instead of spreading equally in every direction, some of that energy becomes concentrated into two narrow outflows. One jet travels away in one direction. The other travels almost exactly opposite it. These jets can move at speeds approaching the speed of light, and once they leave the central region, they can travel much farther than the galaxy's stars. This is where the scale begins changing dramatically. A galaxy is not a solid object with a hard edge. There is no cosmic fence where the last star ends and intergalactic space officially begins. Still, most of the visible stars occupy a recognizable region. A powerful jet can pass through that stellar environment and continue outward into the gas surrounding the galaxy. If it remains active and stable, it can keep going through the wider intergalactic medium. The jet is not simply a long glowing pipe filled with ordinary hot gas. It is a stream of energetic plasma containing electrically charged particles and magnetic fields. These particles can move at relativistic speeds, meaning speeds where Einstein's relativity becomes important. As charged particles move through magnetic fields, especially when energetic electrons spiral around magnetic field lines, they can produce something called synchrotron radiation. That name may sound slightly unfriendly at bedtime, but the concept is straightforward. An electrically charged particle that changes direction emits electromagnetic radiation. Electrons travelling near the speed of light while curving through magnetic fields can radiate strongly across parts of the electromagnetic spectrum, including radio wavelengths. Radio telescopes detect that emission, so when astronomers make an image of a radio galaxy, they are not photographing an enormous cloud glowing red or blue in the way a human eye would see it. They are measuring radio energy arriving from different directions in the sky, then turning those measurements into an image that allows us to see the structure. The colours in many radio astronomy images are added later to represent intensity, frequency, or combinations of observations. Without that translation, your eyes would see absolutely nothing of the radio emission. Human vision is impressive enough for avoiding furniture in a moderately lit room, but it covers only a tiny part of the electromagnetic spectrum. The universe has been doing quite a lot without consulting our eyesight. Radio wavelengths are especially valuable because energetic particles can continue producing radio emission in large structures far outside the galaxy. That lets astronomers trace jets, lobes, and older regions of plasma that may be difficult or impossible to recognize in visible light. And those lobes are one of the most noticeable features of many radio galaxies. Picture the central galaxy in the middle. A jet leaves one side, another jet leaves the opposite side. As those jets travel outward, they carry energy and particles into their surroundings. Far from the galaxy, the flowing material can inflate enormous regions filled with relativistic particles and magnetic fields. These regions are called radio lobes. They can be much wider than the jets that feed them. If the jet is the hose, the lobe is more like the large region where everything delivered by the hose has accumulated and spread out. Except this hose may be hundreds of thousands or millions of light years long, the material can move close to the speed of light, and replacing a damaged nozzle is not especially practical. In some powerful radio sources, astronomers also see hotspots. These are bright regions associated with places where a jet transfers a large amount of energy into the surrounding material. A jet travelling through intergalactic space does not continue forever without consequences. Eventually it interacts strongly with the medium around it. Material can slow, shocks can develop, particles can be accelerated, and bright radio-emitting structures can appear. The result is that a radio galaxy can have several recognizable pieces. There is the central galaxy. There is the compact radio core associated with the active nucleus. There may be narrow jets. Farther out there may be lobes. Bright hotspots can mark intense interactions. And sometimes material flows backward from those regions, creating additional structure around the lobes. Porphyrion shows several of these features on a truly enormous scale. This is part of how astronomers can determine that widely separated patches of radio emission belong to the same system. Because imagine the problem for a moment. You make a radio map of the sky and discover one elongated region of emission. Millions of light years away from it, in the projected image, there is another. Somewhere between them sits a galaxy. Are they connected? Or did several unrelated objects happen to line up from our point of view? Astronomers have to examine the geometry, the radio structure, the central source, the apparent jets, the spectra, the distances, and other observations to build the case that the components belong together. This is especially important for enormous radio systems, because the farther the lobes extend from their host galaxy, the less obvious the relationship can become. A small radio galaxy fits conveniently around its host. A giant one can look as though someone has taken the pieces apart and scattered them across the sky. Finding the centre becomes a little like discovering two garden hoses on opposite sides of a neighbourhood and trying to work out whether they are somehow attached to the same tap. Except the neighbourhood is intergalactic space. One useful clue comes from symmetry. Black hole jets are often produced as a pair, pointing in opposite directions along a common axis. If two radio structures lie on opposite sides of a plausible active galaxy and align with it, that immediately becomes interesting. But nature rarely provides perfect diagrams. Jets can bend. One side can appear different from the other. The environment may be denser in one direction. One lobe may evolve differently. The jets can also be oriented at an angle relative to Earth, which changes how they appear to us. Orientation is important enough that the same basic type of active galactic nucleus can look very different depending on our viewing angle. Suppose a powerful jet is pointing mostly sideways across our field of view, then we have a good chance of seeing the extended radio structure spread across the sky. That is the familiar picture of a radio galaxy. Now imagine a similar system with one of its jets aimed much closer to our direction. Relativistic effects can make that jet appear dramatically brighter. Objects seen under those conditions may be classified differently, including as blazars, depending on their properties. So astronomers have learned that some categories of active galaxies are not necessarily completely different machines. Sometimes we are looking at related engines from different directions. It's rather like seeing a flashlight from the side compared with having someone point it directly into your face. The flashlight has not become a different device. Your experience of it certainly has. Radio galaxies also vary enormously in power and appearance. Some have jets that become broad and diffuse relatively close to their host galaxy. Others maintain narrow, powerful jets over greater distances and produce bright structures toward the outer ends of their radio lobes. These differences tell astronomers about the power of the central engine, the behaviour of the jets, and the environment they're travelling through. That last part matters because no jet grows in isolation. Intergalactic space is extremely empty by everyday standards, but extremely empty does not mean completely empty. There is gas between galaxies. There are particles. There are magnetic fields. Galaxies live inside groups, clusters, filaments, and other large-scale environments. A jet travelling outward has to interact with this material. The surrounding gas can slow it. Pressure can affect its expansion. Density differences can push or distort it. The galaxy itself may be moving through its environment. All of these factors can leave fingerprints in the radio structure. That makes a radio galaxy useful for more than studying the black hole at its centre. Its jets can also act as enormous probes of the space around the galaxy. If a jet bends, something may have influenced it. If one side grows differently from the other, the surrounding environments may not be equal. If the lobes have particular shapes, astronomers can use models to investigate how the system evolved. And if the jets keep travelling for millions upon millions of light years, as Porphyrions did, then we have to ask what sort of conditions allowed them to remain coherent for so long. This is one reason giant radio galaxies are especially interesting. The word giant has a more specific meaning here than simply being impressed by something large. Astronomers have identified a population of radio galaxies whose radio structures extend over enormous physical distances, far beyond the dimensions of their host galaxies. They are useful because reaching those scales usually requires several things to go reasonably well. The central engine must supply energy. The jets have to escape the galaxy. They have to survive interaction with their surroundings. The system needs enough time to grow. And the activity has to produce radio-emitting plasma that astronomers can still detect. There is a simple relationship hiding inside all of this. To build a very long jet system, you generally need both power and time. A jet can move quickly, but not instantaneously. Even something travelling near the speed of light requires millions of years to cross millions of light years. That means structures of this size preserve a history of long-term activity. When we observe enormous radio lobes, we are not seeing something that appeared during a particularly energetic Tuesday afternoon. The system developed over immense periods. The galaxy's central activity may change while this happens. An active nucleus can brighten or weaken. Fuel supplies can vary. Jet production can stop and restart. Older plasma can remain visible after the central engine becomes less active. As a result, radio images can sometimes contain evidence of earlier episodes in a galaxy's life. This makes the phrase radio galaxy slightly more interesting than it first sounds. The radio structure is not just an unusual glow around a galaxy. It can be a record of what the central black hole has been doing and how that activity has affected space far beyond the galaxy. There is another point that can feel surprising. These jets do not generally contain huge fractions of the galaxy's stars or entire planets being thrown outward. We are talking about plasma, particles, energy, and magnetic fields. Yet the amount of energy transported can be enormous. A relatively small region around a supermassive black hole can influence gas on scales vastly larger than itself. This is one of the recurring themes of active galactic nuclei. Something happening near the centre of a galaxy can affect the development of the galaxy as a whole. Energy from an active nucleus can heat surrounding gas. Outflows can disturb material. In some circumstances, this can reduce the rate at which gas cools and forms stars. The central black hole may occupy an almost ridiculously tiny portion of the galaxy's total volume, but its active periods can have consequences far beyond its immediate neighbourhood. Radio jets take that influence even farther. They transport energy outside the main body of the galaxy and into intergalactic space. With ordinary radio galaxies, that is already remarkable. With Porphyrion, the distances force us to think on another scale entirely. Its jets are not merely larger than the galaxy that produced them. They are hundreds of times larger than the familiar stellar disk of a galaxy like our Milky Way. That comparison helps explain why calling the whole 23 million light-year structure a galaxy would give the wrong impression. The host galaxy did not somehow grow until its stars covered 23 million light-years. Its black hole-driven radio structure did. The visible galaxy remains the central home. The radio jets and lobes are the enormous consequence of activity inside it. Think of a lighthouse. The building itself might be small compared with the distance over which its light can be seen. You would not say that the lighthouse is 20 miles wide because its beam reaches a ship 20 miles away. The source and the region influenced by the source are different things. Porphyrion takes that principle and replaces the lighthouse with a supermassive black hole and the 20 miles with millions of light years, which seems a little excessive, but astronomy has never been especially interested in moderation. There is also a useful difference between the light produced by stars and the radio emission produced by the jets. Most of a galaxy's visible light comes from its stars. When astronomers photograph a distant galaxy in visible wavelengths, they are largely mapping where those stars are. Radio observations can reveal an entirely different structure because they trace energetic particles and magnetic fields associated with the active nucleus and its outflows. Place the two images on top of each other and the scale difference can be startling. A relatively compact patch of starlight sits at the centre. Then radio emission reaches outward far beyond it. The galaxy is still there, doing all the things galaxies normally do. Stars orbit, gas moves. Old stars die. New stars may form. Planets, if there are any, continue their business completely unaware that their home galaxy has become an astronomical celebrity because something near its centre has sent plasma across intergalactic space. And somewhere inside all that activity is a black hole that cannot be seen directly. This is what makes the term invisible giant useful for Porphyrion. The enormous structure is not invisible to our instruments. Radio telescopes detect it. But it is invisible to unaided human vision. If we had somehow been looking in precisely the correct direction for all of recorded history, our eyes would never have revealed the full object. The information was arriving. We simply needed the right kind of instrument to notice it. Radio astronomy opened that window. Instead of asking only what the universe looks like in visible light, astronomers began asking what it looks like across the electromagnetic spectrum. And the answer was that the visible universe had been leaving out quite a lot. Cold gas could be traced in radio wavelengths. Pulsars appeared as precise repeating sources. Quasars and active galaxies revealed extraordinary emission. The cosmic microwave background became detectable. Jets and lobes appeared where visible images showed little indication that anything unusual was happening. A night sky viewed entirely in radio wavelengths would not look like the familiar sky above your house. Many ordinary stars would become less important. Other objects would become dramatically more obvious. Supernova remnants would stand out. Pulsars would announce themselves. Active galaxies would fill parts of the sky with structures our eyes never see. And somewhere in an appropriately deep radio map, Porphyrion would stretch across a distance that makes nearly every ordinary galaxy look compact. That does not mean Porphyrion is the brightest radio source in the sky, or something we could pick out using a small antenna in the garden. It is extremely distant. Its great importance comes from what careful observations reveal when astronomers combine sensitive radio surveys with other measurements and determine the physical scale of the system. Distance changes everything. A structure can appear relatively small on the sky, while being physically enormous if it lies sufficiently far away. This is one of astronomy's favourite tricks. Something that looks tiny may simply be very distant. The moon looks approximately the size of a coin held at arm's length, but it would be unwise to try keeping it in your wallet. To understand a radio galaxy properly, astronomers need more than its apparent size. They need to identify the host. They need distance information. They need to understand which radio features belong together. Only then can an angular measurement on the sky be converted into a real physical scale. That is what turned Porphyrion from an interesting radio pattern into a record-setting system. Once its structure and distance were established, astronomers could estimate the distance between its extremes, roughly 7 megaparsecs, about 23 million light-years. The number returns, but now it means more. It is no longer simply a very large distance attached to a strange object. We know what is filling that distance. At the centre is a galaxy. At the centre of that galaxy is an active supermassive black hole. From the region around that black hole, 2 relativistic jets were launched. Those jets carried particles, energy and magnetic fields outward. They travelled far beyond the galaxy. Their activity created enormous radio-emitting structures. Radio telescopes detected those structures billions of years after the light and radio waves began travelling toward us. And by mapping them, astronomers reconstructed the outline of a system far larger than anything the stars of its host galaxy could suggest. There is still one problem, though. Knowing what a radio galaxy is does not make Porphyrion's size easier to understand. How do we understand what a distance like 23 million light-years really means? It is easy to say. 23 million light-years, 4 words and a number. The difficulty begins when you're terribly good at understanding distances that belong to human life. We know what a metre looks like. We can imagine walking a kilometre. We understand that driving a few hundred kilometres takes a while, especially if someone in the car insists that they do not need to stop and then changes their mind 20 minutes later. Even the size of Earth can be understood with a little effort. The planet is about 12,700 kilometres across. Commercial aircraft can carry people across continents in hours. Satellites circle Earth. Humans have travelled to the moon. Then astronomy begins adding zeros. The average distance from Earth to the Moon is about 384,000 kilometers. Light covers that distance in roughly 1.3 seconds. The Sun is much farther away, about 150 million kilometers from Earth. Sunlight takes a little over 8 minutes to reach us. That already gives us a useful way of thinking about astronomical distance. Instead of asking how many kilometers separate two places, we can ask how long light needs to make the journey. Light is the fastest thing we know. In vacuum, it moves at about 300,000 kilometers every second. In 1 second, light could circle Earth more than 7 times. In 1 minute, it travels about 18 million kilometers. In 1 year, it travels roughly 9.46 trillion kilometers. That distance is 1 light year. Now take that distance and repeat it 23 million times. That is approximately the end-to-end extent of Porphyrion's radio jet system. It is not 23 million kilometers. It is not 23 million times the distance between Earth and the Moon. It is the distance light itself travels in 23 million years. Suppose, just for comparison, that a flash of light could begin at one extreme end of Porphyrion and travel straight toward the other end through space. While the light was travelling, 100 years would pass. It would still have almost the entire journey ahead of it. 1,000 years would pass. Still almost nothing. 10,000 years. The light would continue. 1 million years after starting, it would have completed less than 1/20th of the full distance. 10 million years later, it still would not be there. Only after about 23 million years would that beam of light finally cross a distance comparable to the entire observed span of the system. Now compare that with recorded human history. The first cities appeared only thousands of years ago. Agriculture began on the order of 10,000 years ago. Our species, Homo sapiens, has existed for hundreds of thousands of years. All of those timescales are tiny compared with 23 million years. 23 million years ago, humans did not exist. Our genus did not exist. The landscapes of Earth were different. The climates were different, and evolution was working with a very different collection of animals. If light had started crossing a 23 million light-year distance at that time, travelling at the fastest speed allowed by physics, it would only be completing that journey around now. That begins to make Porphyrion's scale a little less like a large number, and a little more like something genuinely difficult to believe. But we can improve the comparison by leaving Earth and moving through the astronomical neighbourhood step by step. Start with the solar system. The distance from the Sun to Neptune is roughly 4.5 billion kilometers, though the exact number changes as planets move around their orbits. That feels enormous from the perspective of a spacecraft. Voyager 2 needed about 12 years to reach Neptune after leaving Earth. Light makes the same journey from the Sun in a little over 4 hours, so already we have something large enough to occupy years of human travel reduced to a few light hours. Porphyrion is 23 million light-years across, not light hours, not light days, not light months, light years. Our entire planetary system becomes essentially invisible on that scale. Even if we include the distant region of icy bodies far beyond Neptune, we are still dealing with something tiny compared with the distances between stars. The nearest star system to the Sun, Alpha Centauri, is a little over 4 light-years away. For everyday astronomy, 4 light-years feels very distant. Our fastest spacecraft would require thousands of years to cross something like that distance using current technology. But against Porphyrion, 4 light-years is almost nothing. You could fit the distance to Alpha Centauri into Porphyrion's 23 million light-year span millions of times. So let's increase the scale again. Our Sun is only one star inside the Milky Way. The Milky Way's familiar stellar disk measures roughly 100,000 light-years across. Now we finally have a unit large enough to make the comparison manageable. 100,000 light-years. That means a ray of light travelling from one side of the Milky Way's stellar disk to the other would need roughly 100,000 years. If some civilization on the opposite side of our galaxy transmitted a message toward us tonight, and the message had to travel something close to the full width of the Milky Way, there would be no question of waiting around for the reply. You would need a very optimistic definition of patience. and yet even our galaxy becomes small compared with Porphyrion. If we use a 100,000 light-year diameter for the Milky Way's stellar disk, then 23 million light-years corresponds to around 230 such diameters. Picture one Milky Way. Place another beside it, then another. Keep doing that until you have hundreds of galaxies arranged edge to edge. Only then do you approach Porphyrion scale. The Discovery team used a somewhat larger reference diameter for the Milky Way and described Porphyrion as comparable to about 140 Milky Ways lined up one after another. The exact number changes depending on where you decide the Milky Way ends, because galaxies do not have solid walls. Their stars thin out gradually, and enormous halos extend beyond the bright disk. Either way, the point remains the same. Porphyrion is not merely a little larger than the Milky Way. It is not twice as large. It is not 10 times as large. Its radio structure extends across a distance requiring well over 100 Milky Way-sized spans, even using a generous definition of our galaxy's diameter. And remember, we are comparing one pair of black hole-driven jets with an entire galaxy containing hundreds of billions of stars. The Milky Way has spiral arms. It has star-forming regions. It contains neutron stars, black holes, nebulae, planets, moons, asteroids, and whatever everyone has forgotten in the back of their kitchen cupboards. Its disk is enormous enough that we have spent our entire existence inside it and have never sent a spacecraft remotely close to leaving the galaxy. Against Porphyrion, the Milky Way is one small unit on a much larger ruler. Perhaps an even more useful comparison is Andromeda. The Andromeda Galaxy is the nearest major galaxy to the Milky Way, around 2.5 million light-years away. On a dark night, under good conditions, Andromeda can actually be seen without a telescope. The faint patch of light reaching your eyes began its journey roughly 2.5 million years ago. When those photons left Andromeda, there were no modern humans looking back from Earth. That distance is already difficult to comprehend. Now, place it against Porphyrion. 23 million light-years is roughly 9 times the distance from us to Andromeda. Imagine travelling from the Milky Way all the way to Andromeda, then doing it again and again and again. 9 journeys of approximately that distance finally put you in the neighbourhood of Porphyrion's full span. This is why calling it a giant radio system does not feel like exaggeration. The jets generated by one active galactic nucleus extend across a distance many times larger than the gulf separating 2 major galaxies in our own local neighbourhood. The central galaxy responsible for Porphyrion is therefore almost comically small in an image of the full radio structure. That does not mean the galaxy itself is small. Observation suggests Porphyrion's host is a substantial galaxy, but the radio system reaches so far beyond it that the host appears as a tiny central feature compared with the total length of the outflow. You could think about a seed growing roots that stretch across several countries, except even that comparison fails almost immediately because countries remain annoyingly small. Scale comparisons always begin breaking down when we reach objects like this, so astronomers use megaparsecs. A parsec is another astronomical distance unit, equal to about 3.26 light-years. A kiloparsec is 1,000 parsecs. A megaparsec is 1 million parsecs, which works out to about 3.26 million light-years. Porphyrion spans roughly 7 megaparsecs. Astronomers like megaparsecs because at the scale of galaxies and cosmology, light-years begin producing numbers with too many zeros. Saying 7 megaparsecs is considerably easier than repeatedly saying 22-point-something million light-years. It also makes Porphyrion's significance clearer to people who study the large-scale universe. 1 megaparsec is already a distance associated with relationships between galaxies. Several megaparsecs takes us firmly into the territory of galaxy groups, cluster environments, filaments, and large-scale cosmic structure. A radio jet reaching 7 megaparsecs is no longer simply affecting the immediate surroundings of its host galaxy. It is operating on what astronomers call cosmological scales. That was one reason the discovery was so surprising. Before Porphyrion, the known size range of confirmed black hole jet systems seemed to stop around 5 megaparsecs. 5 megaparsecs is already enormous, about 16 million light-years. The previous record holder, Alcyonius, had demonstrated that a radio galaxy could reach roughly that territory. Then Porphyrion extended the known limit to about 7 megaparsecs. An extra 2 megaparsecs may sound modest until we convert it back. 2 megaparsecs is about 6.5 million light-years. Porphyrion exceeded the earlier 5 megaparsec scale by a distance greater than the separation between the Milky Way and Andromeda, twice over. That extra portion alone would be considered an extraordinary astronomical distance. For Porphyrion, it is merely the amount by which the record had to be extended. There is another complication when astronomers measure something like this. We observe the universe projected onto the sky. Space is three-dimensional, but a telescope image gives us an apparent structure across 2 dimensions. Imagine holding a pencil sideways. You see its full length. Now slowly point the pencil toward your eye. The pencil has not become shorter, but its apparent length decreases. A black hole jet can have the same problem. If a jet system lies mostly across our line of sight, we can observe something close to its actual physical extent across the sky. If it points significantly toward us or away from us, its projected length can be shorter than its real length. So measurements of giant radio systems involve questions about geometry as well as distance. The quoted roughly 23 million light-years for Porphyrion describes its enormous observed physical span based on the radio structure and the distance to its host. The true three-dimensional geometry may add further complexity, but astronomers do not need Porphyrion to be made any larger for it to become interesting. 7 megaparsecs is enough, more than enough really, and length is only one part of the puzzle. A jet system is not like placing a rigid rod into space. Porphyrion had to grow. The central engine had to operate. Energy had to travel outward. The jets had to push through their environment. The radio-emitting particles we detect had to reach extraordinary distances from the galaxy where the process began. That means 23 million light-years is also evidence of persistence. Something near the central black hole kept supplying a system capable of reaching far beyond its home. It is tempting to imagine the 2 jets being created instantly at their full length, because telescope images show us the entire structure at once. Nature did not build them that way. The material had to propagate outward, the lobes had to develop. Interactions occurred along the route. Energy was deposited into surrounding space. The full system accumulated over a very long period. Even a jet moving close to light speed cannot create a 23 million light-year end-to-end system overnight, and the leading edges of radio jets do not simply cross the intergalactic medium at the speed of light without resistance. They interact with surrounding material and transfer energy to it. The detailed history is complicated, but the scale alone tells us that the central activity lasted long enough, or occurred in a pattern effective enough, to produce something extending for millions of light-years in 2 directions. Now at the age of the universe at the time, Porphyrion is not a nearby system living in the relatively mature cosmos around us today. We see it as it existed when the universe was roughly 6.3 billion years old. Today, the universe is about 13.8 billion years old. The signal from Porphyrion has taken around 7.5 billion years to reach us. We are therefore looking at a structure that achieved this remarkable size when the universe was less than half its present age. That matters because the universe was denser then. Galaxies and large-scale structures were packed closer together. The intergalactic environment was different. According to the Discovery study, the universe during the relevant period was several times denser than it is today. You might expect an enormous jet to have an easier time growing through an emptier modern universe. Instead, Porphyrion managed to reach 7 megaparsecs at an earlier epoch, when the conditions should have made maintaining such an organized system especially challenging. This is where its length stops being a record for the sake of a record. Suppose someone built the world's longest bridge. The number would be interesting, but engineers would immediately ask how the bridge supports its weight, what materials were used, how wind affects it, and why it does not collapse. Porphyrion produces the same kind of scientific reaction. 23 million light-years is the headline. The real question is how? How does a pair of jets stay coherent over that distance? How much power must the central engine provide? How long was it active? What kind of environment did the jets pass through? Why were they not disrupted much earlier? How many similar systems existed but have faded beyond our ability to detect them? And if jets can really reach these scales, what have they been doing to the rest of the universe? The last question becomes especially important when we compare Porphyrion with the cosmic web. On the largest scales, matter in the universe forms a network of filaments, clusters, and voids. Galaxies gather along the denser filaments. Clusters sit where structures intersect. Between them are enormous regions containing far less matter. Porphyrion's reported span is comparable with meaningful portions of those structures. The Nature study estimated that its 7 megaparsec extent is about 2/3 the radius of a typical cosmic void at that era. A jet originating in one galaxy could therefore reach far outside its immediate local environment. That is very different from imagining a black hole affecting only the stars and gas near the centre of its own galaxy. Porphyrion suggests that black hole activity can transport particles, magnetic fields, and energy across distances associated with the architecture of the cosmic web. One galaxy starts the process. The consequences may extend millions of light-years away. Scale can be deceptive here because the black hole responsible for the jets occupies such a tiny region compared with the resulting structure. Shrink Porphyrion's entire 23 million light-year span until it fits across a large room. The host galaxy would become difficult to represent visibly. Shrink it onto the length of a table, and the region containing the central black hole would be effectively microscopic. Yet activity near that tiny centre is responsible for the structure stretching from one end to the other. Astronomy repeatedly gives us this mismatch. A star can influence objects billions of kilometres away. A supernova can send material across interstellar space. A galaxy can disturb neighbouring galaxies through gravity. A black hole can power jets vastly larger than its host galaxy. Porphyrion is simply one of the most extreme examples we have found. It also shows why size in astronomy has to be handled carefully. When someone calls Porphyrion 23 million light-years across, it is easy to imagine a galaxy filled with stars across that entire distance. That is not what astronomers observed. The host galaxy is not a 23 million light-year wide collection of stars. The measurement belongs to the radio jet structure associated with its active central black hole. That distinction actually makes the system more impressive. A single galaxy produced an outflow whose reach dwarfs the galaxy itself. The visible population of stars occupies the centre. The radioactivity extends outward for millions of light-years on both sides. This also means that record labels can be confusing. The largest galaxy by stellar diameter is a different question from the largest radio galaxy, the largest black hole jet system, the largest galaxy cluster, or the largest structure in the universe. Astronomers measure different things for different reasons. Porphyrion's record is tied to its paired radio jets. That is where the famous 23 million light-year number comes from. It is a record in reach, and reach may turn out to matter more than the record itself. Before instruments such as LOFAR began mapping enormous areas of the radio sky with high sensitivity, structures like Porphyrion were difficult to discover. Their radio emission can be faint and spread across large regions. The host galaxy may appear tiny between widely separated lobes. Even recognizing that distant pieces belong to one system takes careful analysis. The more thoroughly astronomers search, the more giant radio galaxies they find. Thousands have now been identified in modern surveys. That immediately raises the obvious possibility that Porphyrion will not remain the record holder forever. Perhaps there is a 30 million light-year system waiting in existing data. Perhaps there is a 40 million light-year structure so faint that nobody has connected its pieces yet. Perhaps Porphyrion really is close to some physical upper limit. We do not know. That uncertainty is more useful scientifically than simply announcing that we found something big. Every new extreme object tests our assumptions about what nature can produce. If our models tell us jets should usually break apart before reaching a certain size, and then we find one larger than that, we have learned something. Maybe the environment was unusually favourable. Maybe the jet was unusually powerful. Maybe the source remained active for an unusually long time. Maybe magnetic fields helped stabilise the flow. Maybe the old assumptions were based on an incomplete sample. Porphyrion does not provide all the answers merely by existing. It provides a very large problem that the answers now have to explain. And after moving outward through all these scales, from Earth to the solar system, from nearby stars to the Milky Way, and from the Milky Way to the spaces between galaxies, we can finally return to the small point in the middle. The next question is not how large Porphyrion became. We have stretched our mental ruler about as far as it is willing to go. The more useful question is what kind of engine can do this. The entire 23 million light-year structure begins in a place so small by comparison that, on a map showing all of Porphyrion, the central engine would be impossible to draw to scale. At the midpoint of Porphyrion lies the galaxy identified as J15293 2.1 6 plus 6 01 53 4.4. It is not a small galaxy. The observations used in the Discovery study indicate a stellar mass of roughly 670 billion times the mass of the Sun, making it several times more massive than the Milky Way and stars. Spectroscopy with a Keck 1 telescope measured a redshift of about 0.896, placing the galaxy in the universe we see from billions of years ago. And somewhere in the centre of that galaxy is the supermassive black hole associated with Porphyrion's extraordinary jets. It is tempting to imagine an object worthy of the structure it produced. A black hole thousands of times larger than every other black hole. Something so extreme that astronomers took one look at it and immediately understood why Porphyrion became so large. But that would be getting ahead of the evidence. The central black hole's mass has not been directly established in the same way Porphyrion's radio structure has been measured. We know that the host contains an active supermassive black hole, and the energy involved tells us that it must be a formidable engine, but we should not simply attach a dramatic mass to it because the jets are dramatic. A bigger radio structure does not automatically mean the biggest black hole. This is useful because black holes have acquired a slightly misleading reputation. Whenever something unusually energetic happens in a galaxy, the black hole often gets described as though it were performing the event by brute force. But a black hole sitting alone does very little. Place an isolated black hole in empty space with no matter nearby, and there is no bright accretion disk, no luminous active nucleus, and no enormous radio jet. The black hole provides the gravitational environment. The activity depends on what surrounds it. Porphyrion's central engine worked because matter was available to fall toward the black hole. Gas approaching a supermassive black hole usually cannot drop directly inward. It carries angular momentum, so it begins orbiting. Material moving at different speeds interacts. Magnetic fields become tangled and amplified, and the gas forms a rotating accretion flow around the central object. The closer that material gets, the more extreme the conditions become. Orbital speeds increase, temperatures rise, magnetic fields can become extraordinarily strong. Matter in the inner region can release an enormous amount of energy before some of it finally disappears beyond the event horizon. That last point matters. The black hole is not producing energy from nothing. The system is converting energy associated with infalling matter, and potentially the black hole's rotation, into radiation and powerful outflows. Gravity is doing very serious accounting. Matter falls deeper into the gravitational potential, and a fraction of its available energy can emerge before the matter is lost behind the event horizon. This is why accreting black holes can become so luminous. Nuclear fusion makes ordinary stars shine. In the Sun, hydrogen nuclei combine to form helium, and a small fraction of mass is converted into energy. Accretion onto a black hole can be even more efficient at converting available mass into radiation. That means a region much smaller than a galaxy can temporarily outshine the combined starlight of the galaxy around it. When this happens around a supermassive black hole in the centre of a galaxy, we call the system an active galactic nucleus. And Porphyrion's central source turned out to be a particularly interesting kind. Observations indicated that its active nucleus was operating in what astronomers call a radiative mode. This was notable because many enormous radio systems in the nearby universe are associated with another form of black hole activity, often described as jet mode. Porphyrion showed that a radiatively efficient active black hole could also be associated with jets reaching extraordinary distances. The names are not especially friendly, so it helps to slow them down. An active black hole needs fuel. Depending on how that fuel arrives and how efficiently the accretion flow releases radiation, the nucleus can behave in different ways. In a radiatively efficient system, substantial energy emerges as the electromagnetic radiation from the material falling toward the black hole. The accretion disk can become extremely luminous. Gas around the central region can be ionized. The object may show strong optical emission lines and other signs that matter is being supplied efficiently to the black hole. At the same time, some active nuclei can launch powerful jets. There is no rule saying a black hole must choose between being bright and having a jet. The relationship between accretion, black hole spin, magnetic fields, and jet production is much more complicated than a simple switch. Porphyrion is a very good reminder of that. For a long time, the largest radio galaxies tended to be associated with systems whose black holes were operating at relatively low accretion rates in a jet-dominated state. That made some sense. To grow a radio structure over enormous timescales, perhaps you wanted a black hole quietly producing jets for a very long period without consuming fuel in a more luminous phase. Porphyrion does not fit comfortably into that simple picture. Its host showed evidence of a radiatively efficient active nucleus, meaning the central black hole was not merely producing mechanical jets while remaining otherwise faint. The engine was actively accreting. This is one of those details that turns a large object into a useful scientific problem. The size alone is impressive. The type of engine producing that size tells us something about how incomplete our assumptions may have been. There is another unusual fact about the host. Porphyrion does not appear to sit in the centre of a rich galaxy cluster. That is important because clusters contain enormous quantities of hot gas, and the radio galaxies living inside them interact strongly with that environment. The Discovery study instead found that Porphyrion's host was probably associated with a filament of the cosmic web, with lower density regions surrounding it in many directions. The researchers suggested that jets travelling into progressively thinner environments may have had a better chance of remaining stable over immense distances, but before a jet can survive intergalactic space, it has to be launched. And this is where the black hole becomes less like a cosmic drain and more like one component of an enormous electromagnetic machine. Imagine matter spiralling toward the centre. It forms an accretion flow around the black hole. The material is not made of quiet little particles politely orbiting in neat circles. It is plasma. Electrons and atomic nuclei move through an environment dominated by enormous gravitational forces, high temperatures, turbulence, and magnetic fields. Because plasma carries electric charge, magnetic fields can strongly influence its motion. The rotating accretion flow stretches and twists those fields. Near the black hole, magnetic field lines can become organized around the rotation axis. Under the right conditions, energy is directed away from the central region, along those magnetic structures. Two outflows form, one above the disk, one below it. The system begins producing jets. The details are still being studied, and there are different mechanisms that may contribute. One important idea is that a rotating black hole can transfer some of its rotational energy to magnetic fields threading the region around it. Another involves energy and matter from the accretion disk itself. Real systems may use a combination of processes. The result, however, is something astronomers observe repeatedly across the universe. A compact central object only a tiny fraction of a light-year across can produce jets reaching thousands, millions, or in Porphyrion's case, many millions of light-years. And those jets are narrow. That may be the most important part. Producing an explosion is one thing. Producing a directed beam is another. If Porphyrion's central black hole had simply released the same energy equally in every direction, it would not have created two long opposing radio structures. It would have heated and disturbed the surrounding gas in a much more spherical fashion. Instead, the engine concentrated a large fraction of its mechanical output into two preferred directions. That concentration allowed the energy to travel. A useful comparison is the difference between switching on a light bulb and switching on a laser. Both release electromagnetic energy. One spreads its light broadly. The other sends energy into a narrow beam. Black hole jets are not lasers, of course, but the comparison helps explain why collimation matters. When energy is confined to a narrow outflow, it can remain effective much farther from the source. Porphyrion required this directional control on a scale that is difficult to overstate. The Discovery team's dynamical modelling estimated a combined jet power of about 1.3 times 10 to the 39 watts. That is 1 followed by 39 zeros in watts. Converted into a friendlier comparison, the power is equivalent to the radiant output of trillions of suns. Caltech described the two outflows as carrying a total power comparable with trillions of stars like ours. And this was not a brief burst. The same modelling suggested an age of around 1.9 billion years for the outflow, although there is considerable uncertainty in reconstructing the history of a system this distant and complex. That number creates a very different mental picture of the central engine. When people hear the word jet, it is easy to imagine a sudden event. A black hole switches on. Two beams shoot outward. A few dramatic moments later, Porphyrion exists. But giant radio systems develop over geological and cosmological timescales. The central engine has a history. The amount of material reaching it can change. The jet power can change. The environment can change. The galaxy itself continues evolving. The black hole grows. The accretion flow responds to new supplies of gas. Everything in the system is moving while the radio structure expands. Modelling Porphyrion therefore involves reconstructing a process that unfolded over an enormous fraction of the age of the universe at that time. If the estimated age is roughly correct, the jets could have been developing for longer than complex animals have existed on Earth. That should probably make any complaint about a slow internet connection feel slightly less serious. There is also an interesting question hiding inside the word fuel. Where did the black hole get enough material to remain active? A galaxy with hundreds of billions of solar masses in stars contains plenty of matter, but most of those stars are not falling into the central black hole. A black hole does not simply vacuum up an entire galaxy. Stars orbit the galactic centre, and most continue doing so safely for billions of years. Even stars relatively close to the black hole can remain in stable orbits. What matters for accretion is gas that loses enough angular momentum to move inward. That can happen through many processes. Gas clouds can collide. Instabilities inside a galaxy can redistribute angular momentum. Interactions with other galaxies can disturb gas. Mergers can send material toward the central regions. Bars and other structures can help move gas inward across different scales. Eventually, some fraction of that material may reach the region where the black hole's gravity dominates. This is why feeding a supermassive black hole is partly a galaxy-scale problem. The event horizon may be tiny compared with a galaxy, but getting gas from tens of thousands of light-years away down into the central region requires a chain of events. It is like trying to deliver dinner to someone sitting at the bottom of a rapidly spinning funnel. The food is available. Getting it to the correct address is the difficult part. Once material reaches the accretion flow, another problem appears. A powerful jet requires more than fuel. It requires magnetic organization. A turbulent disk can drag magnetic field lines inward. Under certain conditions, magnetic flux can accumulate close to the black hole. If the black hole is rotating, the interaction between that spin and the magnetic field can provide an enormous reservoir of energy for a relativistic jet. Black hole spin is therefore potentially important. Supermassive black holes can rotate very rapidly. Unlike a solid planet, a black hole has no surface rotating in the ordinary sense, but a spinning black hole changes the geometry of space-time around it. Close enough to the event horizon, space-time itself is dragged around the rotating black hole. Physicists call this frame dragging. Magnetic fields interacting with this rotating system can help extract energy and send it outward. The physics becomes mathematically complicated very quickly, but the practical outcome is easy to recognize in telescope images. A galaxy develops two jets. Those jets can be much brighter at radio wavelengths than the galaxy would otherwise be, and the energy source ultimately traces back to matter falling inward and, potentially, energy stored in the rotation of the black hole. There is an almost annoying efficiency to it. Matter moves toward the centre, some disappears into the black hole, but before it does, the environment can redirect an astonishing amount of energy outward. Something falls in, and something else is launched away at relativistic speeds. Black holes, therefore, do not merely remove matter from the universe around them. Active black holes can be extraordinarily effective at returning energy to that universe. This process is known broadly as black hole feedback, and feedback has consequences. Energy released by an active nucleus can heat gas inside a galaxy. Jets can push gas around. Shockwaves can form. Material that might otherwise cool and form stars can be disturbed or heated. In some situations, outflows may remove gas from regions where stars could have formed. In others, compression from a jet may help trigger localized star formation. The relationship is complicated enough that astronomers still spend a great deal of time trying to understand exactly when active black holes suppress star formation and when their effects are more mixed. Porphyrion pushes the feedback question well outside the host galaxy. Most discussions of black hole feedback focus on what happens inside a galaxy, or in the halo surrounding it. Porphyrion carried energy millions of light-years beyond those scales. The Discovery team's modelling estimated that the jets transported on the order of 10 to the 56 joules of energy into the intergalactic medium over their lifetime. That is not energy sitting inside the event horizon. It is energy delivered outward. Particles were accelerated, magnetic fields were transported, shocks moved through surrounding gas. The central black hole influenced an environment enormously larger than the galaxy containing it. This is why calling the black hole the heart of Porphyrion is useful only as long as we remember that it did not work alone. The galaxy provided the setting, gas provided fuel, the accretion flow processed that fuel, magnetic fields helped organize the outflow, the rotating central system supplied energy, the surrounding intergalactic medium determined how the jets developed once they escaped. Porphyrion is the result of all of those pieces working together. Take away the fuel, and the active nucleus fades. Take away the magnetic structure required to produce a powerful jet, and the energy may emerge differently. Place the same jet in a much denser environment, and it might be disrupted long before reaching anything close to Porphyrion's size. Change the history of the galaxy, and the black hole might never have entered the same active state at all. This helps explain another important point. We should not picture Porphyrion's central black hole as continuously blasting at precisely the same output for billions of years, like a perfectly maintained engine in a laboratory. Astrophysical systems fluctuate. Accretion rates change. Jets can vary in power. Activity can weaken and restart. The large radio structure preserves the accumulated result of a long history, rather than providing a second-by-second record of perfectly steady behaviour. What astronomers observe now is also affected by distance. We are not watching the central black hole live. The radiation reaching our telescopes left the system billions of years ago. We're reconstructing an ancient period of activity from photons and radio waves that have crossed the expanding universe to reach Earth. Even within Porphyrion itself, there is no single universal snapshot in the everyday sense. The structure is millions of light years long, so light from different parts follows different paths to us. When astronomers model such a system, geometry and travel time matter. The radio image may look like one object displayed at one moment, but the underlying reality is a large evolving system whose different regions are separated by distances that light itself needs millions of years to cross. Back at the centre, though, one clue remains particularly important. The jets point back toward the host galaxy. High-resolution radio observations show that the main jet axis passes through J15293 2.16 plus 6 0153 4.4, helping identify it as the source rather than another nearby radioluminous active galaxy seen close to the same line of sight. Follow-up observations strengthen that identification, connecting the enormous outer radio structure to the active nucleus inside this massive host. That may sound like a small observational detail, but it was essential. Finding two enormous radio lobes does not automatically tell you which galaxy produced them. When the structure covers millions of light years and the field contains more than one active galaxy, astronomers have to trace the evidence inward. The alignment matters, the radio core matters, the spectral behavior matters, the optical spectrum matters, the distance matters. Only when those pieces agree can researchers confidently point to one galaxy and say that this is where the outflow began. Porphyrion's trail led to J15293 2.16 plus 6 0153 4.4. Then the problem became more interesting. The host was massive. The nucleus was radiatively active. The jets carried extraordinary power. The outflow had survived for an immense amount of time, and the two sides remained aligned across a distance approaching the scale of the cosmic web. Launching a jet near a black hole is already difficult physics. Keeping that jet narrow and recognizable after it leaves the galaxy is a completely different challenge. Near the center of the galaxy, the conditions are extreme enough to explain why powerful outflows can form. Matter is falling toward a supermassive black hole. Plasma is moving rapidly through an accretion flow. Magnetic fields are being stretched, twisted, and organized. Enormous amounts of energy are available in a very small region. Then the jets leave, and suddenly they have to survive the universe outside. That may sound easy because we often describe intergalactic space as empty. If there is almost nothing out there, perhaps a jet can simply keep moving until the black hole stops supplying it. Unfortunately for the jet, almost empty is not the same thing as empty. A radio jet leaving an active galaxy has to travel through layers of material. First, it moves through the environment of the galaxy itself, then through the gas surrounding the galaxy. Farther out, it enters the intergalactic medium, the thin material spread between galaxies. Beyond that, it may encounter the much larger structure of the cosmic web. None of these regions resembles Earth's atmosphere. The densities are extraordinarily low by everyday standards. You would not notice a breeze. You could not gather enough gas for a useful cup of tea without being prepared to wait a very long time. But a jet extending millions of light years encounters an enormous volume of space. Tiny interactions repeated across enormous distances become important. This is especially true because the jet is not a solid object, it is plasma. That means it is made of electrically charged particles, together with magnetic fields and energy, moving in a highly organized flow. A metal sphere might remain narrow because the atoms making up the sphere are physically bound together. A black hole jet has no rigid walls, there is no pipe around it. Nothing has been manufactured to keep the contents inside. The jet has to maintain its shape through the behavior of the moving plasma, the magnetic fields within it, its pressure, its speed, and its interaction with the material around it. For Porphyrion, that organisation persisted across an extraordinary distance. This is one of the reasons the system is more interesting than simply being long. Imagine spraying a narrow stream of water from a hose. Close to the nozzle, the stream may remain fairly tidy. Farther away, it begins to spread and break apart. Air resistance, turbulence, gravity, and irregularities in the flow eventually destroy the neat stream. Now remove the garden hose, replace the water with relativistic plasma, replace the garden with intergalactic space, and continue the experiment for millions of light years. The comparison is not physically exact, but the basic problem remains. How does a moving stream remain a stream? At the beginning, the jets are believed to leave the central region at relativistic speeds, meaning substantial fractions of the speed of light. That enormous velocity helps them travel outward. Their narrow shape also matters. If the energy from the active nucleus spread equally in every direction, it would become diluted rapidly as it moved away from the galaxy. A jet concentrates energy into a relatively small cross-sectional area. That concentrated flow can push much farther into its surroundings. Think about walking through deep snow. If you lie flat and try to move the entire width of your body forward through the snow at once, progress is difficult. If you push a narrow pole through it, the pole can penetrate much farther because the force is concentrated over a smaller area. A jet does something vaguely similar. Its energy and momentum are directed along an axis. That allows the leading part of the flow to push against the surrounding medium. But the jet does not pass through that medium without disturbing it. At the advancing end, material has to move somewhere. The jet can drive shocks into the surrounding gas. Plasma flowing along the jet may encounter the region near the front and slow abruptly. Energy that had been carried forward becomes deposited into the surrounding region. Particles can be accelerated, magnetic fields become involved, radio emission is produced, and in some systems this creates a bright feature called a hotspot. Porphyrion has evidence of this sort of structure, particularly on its southern side. The observations identify a southern jet, an inner hotspot, and a more distant outer hotspot associated with a backflow. A hotspot is useful because it gives us a clue about what the jet is doing at a particular location. The material is not simply fading gently into space. There is an active interaction. A large amount of the jet's energy is being processed in a relatively concentrated region. Then some of the plasma can move away from the hotspot without simply continuing straight forward. It can flow backward along the outside of the advancing jet. This is the backflow. That sounds strange at first. The black hole launches material outward. The jet travels away from the galaxy, and then some plasma near the far end begins moving back toward the center. But the flow is responding to pressure. When the narrow jet deposits energy near its working surface, that energy inflates a much broader region around it. The resulting radio lobe can contain energetic particles and magnetic fields delivered by the jet over long periods. The jet is the narrow supply route. The lobe is the much larger region built from everything the jet has transported and disturbed. If the end of the jet is continuously delivering new plasma into a confined region, some of that material can spread sideways and backward. The result can resemble a narrow river entering a broad reservoir, except the river is travelling at relativistic speeds, and the reservoir may extend across distances larger than galaxies. This helps explain why radio images do not show Porphyrion as two perfectly thin lines running outward from a dot. There are narrow features, wider lobes, bright regions, and changing structures along the system. The jets have a history. The shapes record interactions that took place as the outflow grew, and growth is the important word. Porphyrion did not simply fire two particles into space and wait until they travelled 23 million light-years apart. A radio source develops as the central engine continues delivering energy. The jets advance through the surrounding medium. Their leading regions push outward. Lobes inflate behind them. Pressure builds inside those lobes. Older plasma remains behind as newer material arrives. The entire structure evolves together. One useful way to picture this is to imagine a tunnel being driven through difficult ground. The machine at the front advances, material is moved, a larger passage develops behind it. The operation continues as long as power and resources are supplied, but a radio jet does not have steel reinforcement lining the tunnel. It has to create its own conditions for survival. The lobes themselves may help. A powerful jet can inflate a cocoon of hot, low-density plasma around its path. Once that cocoon exists, later jet material may travel through an environment that is easier to cross than the undisturbed material outside. Instead of continually forcing its way through fresh intergalactic gas along its entire length, the inner part of the jet is moving through a region already altered by earlier activity. That does not solve every problem. It may create new ones, but it helps us understand why the surrounding radio structure is not merely a byproduct. The jet modifies the route through which it travels. In effect, the outflow changes its own environment. The leading edge still has to confront material that has not yet been disturbed. That is where much of the difficulty lies. The farther the system grows, the longer the connection between the central engine and the advancing ends becomes. Porphyrion's full radio structure stretches roughly 7 megaparsecs. The black hole at the centre is therefore feeding a system whose outer regions are separated from it by millions of light years. Nothing about that connection can update instantaneously. Information cannot travel faster than light. Changes near the black hole take time to propagate outward. The outer radio structure is responding to activity that began long before conditions in the central engine reached the state we would observe at a later moment. A jet system of this size is not one machine operating according to one common clock. It is a long chain of cause and effect stretched across cosmic distances. That makes Porphyrion's straightness particularly interesting. Even a small change in direction near the centre can become a large displacement far away. Imagine pointing a laser at a wall 1 meter from you. Move your hand by a tiny angle, and the spot moves slightly. Now imagine that wall is millions of light years away. A small change in direction becomes enormous. So if the orientation of Porphyrion's engine had wandered dramatically over time, we might expect the resulting radio structure to curve, spread, or occupy a much broader region. Instead, the system maintains a remarkably extended overall axis. That does not mean it is mathematically straight or perfectly symmetrical. Real radio galaxies rarely behave that politely. But the central engine and the jet system remained organized well enough to create 2 opposing structures whose relationship is still recognizable across roughly 23 million light-years. The challenge becomes greater when we consider instability. A fast, light fluid moving through a denser surrounding fluid can develop disturbances. Different parts of the flow move at different speeds. The boundary between jet material and external gas can become unstable. Small irregularities can grow. Turbulence can develop. Magnetic fields can twist and reorganize. The jet can broaden, bend, slow, or break apart. Some of these effects are related to the same broad kinds of fluid instabilities we see in much more familiar settings on Earth. Clouds develop curling edges. Smoke forms rolling patterns. Ocean waves grow where moving fluids meet. When one fluid pushes into another, complicated shapes appear. Plasma jets introduce magnetic fields and relativistic speeds on top of all that, which is nature's way of making sure the mathematics does not become too relaxing. Researchers studying Porphyrion specifically emphasize this problem. The jets demonstrate that black hole outflows can avoid destruction by magnetohydrodynamic instabilities across cosmological distances. Magnetohydrodynamics is the study of how electrically conducting fluids, such as plasma, behave in the presence of magnetic fields. The word is considerably longer than the basic idea. The plasma moves. The magnetic fields affect that motion. The moving plasma also affects the magnetic fields. Everything reacts to everything else. Inside a jet, Those interactions can help guide and organize the flow, but they can also produce instabilities. A jet can develop helical distortions. Its boundary can become turbulent. Different regions can mix. Over enough distance, small disturbances may become large enough to destroy the narrow relativistic flow. This is why Porphyrion presents a genuine theoretical problem. For decades, observations of the largest known black hole jet system seem to reach a rough upper range around 5 megaparsecs. Theoretical work also suggested that maintaining jet stability beyond those scales would be difficult. Then Porphyrion appeared at about 7 megaparsecs. Nature had apparently not received the 5 megaparsec memo. It is worth being careful here. Porphyrion does not prove that there is no physical limit, and it does not tell us exactly which process kept its jets coherent. The researchers who reported the system explicitly said that how jets can preserve coherence for so long remains unknown. There are plausible ingredients. High jet power can help. Magnetic fields may help stabilize parts of the flow. The density of the surrounding environment matters. The geometry of that environment matters. A jet expanding into progressively thinner material may have an easier time advancing than one attempting to cross dense gas. But none of those observations allow us to point to one simple trick and say, that is how Porphyrion did it. The universe has provided the result before providing the full explanation. That happens rather often. One environmental clue may be especially important. Porphyrion existed when the universe was much denser than it is today. At first, this seems like bad news for a jet trying to become enormous. Denser surroundings should provide more material to push through. More interaction creates more opportunities for the jet to lose energy or become disrupted. Yet the large-scale environment around the host may have offered favourable routes. The host appears associated with a filament of the cosmic web rather than sitting deep inside a rich, dense galaxy cluster. And around cosmic filaments are lower density regions. A jet launched in a favourable direction may move away from the denser filament and into increasingly thin intergalactic material. Think about trying to walk through a crowded room. At the centre, you keep bumping into people. Near the doorway, the crowd thins. Once outside, progress becomes much easier. If Porphyrion's jets found something resembling a low-density route away from their host environment, that could have helped them grow. The comparison should not be taken too literally. There are no cosmic doorways with green exit signs, but density gradients matter. A jet pushing into dense gas encounters more resistance than one entering thinner gas. The environment on the two sides can also differ. This helps explain why twin jets are not always twins in appearance. They share a central source, but they travel through different regions of space. One side may encounter denser material, the other may enter a lower density environment. One may advance more easily. One may produce a brighter hotspot. Magnetic fields and particle populations can evolve differently. Orientation relative to Earth can also change how bright each side appears, because the plasma moves at relativistic speeds. So two jets launched from the same black hole do not necessarily become mirror images. Porphyrion itself is asymmetric. Its observed northern and southern structures are not carbon copies. That is expected in a real cosmic environment. If anything, perfect symmetry over millions of light years would be more suspicious. Space is not an empty sheet of graph paper. It contains structure. The jets have to respond to it. Their ability to cross those environments also depends on momentum. A powerful relativistic jet carries substantial momentum along its direction of travel. When it encounters surrounding gas, that forward momentum helps drive the advancing region outward. But the front of the radio source generally moves much more slowly than the individual particles racing through the inner jet. This distinction is important. Imagine cars travelling quickly along a road toward a construction project. The cars may move at high speed along the open road. The construction site itself does not move forward at the same speed as the cars. The cars arrive, deliver workers and materials, and the project advances gradually. Something roughly comparable happens in a powerful radio source. Plasma can stream down the jet at relativistic speeds. At the far end, that flow supplies energy and momentum to a region pushing into the intergalactic medium. The front advances, but not at the same speed as the fastest material inside the jet. This means building a multi-megaparsec radio structure can take a very long time, even though the plasma inside the jets moves extremely quickly. Porphyrion therefore required persistence in addition to power. A short-lived central outburst could produce a bright jet. It would struggle to build a structure stretching 7 megaparsecs unless the activity lasted long enough, or repeated episodes maintained the larger system. The outflow also had to remain supplied while the outer lobes continued evolving. This creates a second kind of survival problem. It is not enough for the jet material to avoid becoming unstable. The central engine must continue doing something useful for long enough. Supermassive black holes do not feed at constant rates forever. Their fuel supply changes. Gas can run low. The accretion flow can alter its state. Jet production can weaken. The direction of the system can shift. A galaxy interaction can disturb the central environment. Yet giant radio structures show that some active nuclei can maintain or repeatedly restore the conditions needed for large-scale outflows over immense spans of time. Porphyrion is the extreme example we currently know. The fact that its host contained a radiatively efficient active nucleus makes the story even more interesting. This was not simply a weak central source connected to some ancient detached radio relic. The observations tied the enormous jets to an active system capable of substantial radiative output. Somehow the engine, the jet, and the environment combined to produce a structure reaching farther than any confirmed black hole jet pair previously known. Once a jet reaches those distances, it no longer affects only its own galaxy. It begins carrying the influence of the central black hole into the intergalactic medium. Every shock deposits energy. Every lobe contains energetic particles. Magnetic fields that originated or were amplified near the central system can be transported far from the host. Atomic nuclei can be carried outward. The surrounding gas can be heated and displaced. A black hole sitting in one galaxy begins altering regions of space that are no longer meaningfully part of that galaxy. This is the strange consequence of collimation. The central engine is compact. The outflow is narrow. Because the energy is concentrated, its influence travels far. Then, at the distant ends, the energy spreads again. Lobes inflate. Hotspots process incoming plasma. Backflows carry material into broader regions. A narrow jet becomes a large footprint. The cosmic searchlight comparison works in that sense. A lighthouse does not illuminate only the building containing the lamp. It directs energy outward along a preferred path. The farther the beam travels, the larger the region it can reach. But black hole jets do more than illuminate. They physically transport particles, momentum, magnetic fields, and energy. They can reshape the material they encounter, and unlike a lighthouse beam, they leave something behind. Long after an individual parcel of plasma has passed through the inner jet, radio-emitting particles can remain in the lobes. Those particles lose energy over time. The radio emission changes as the population ages. The lobes expand and mix with their surroundings. Eventually, after the central engine weakens, the radio structure can fade. This raises an interesting possibility. The systems we detect may represent only the visible portion of a much larger history of black hole activity. Some ancient giant jets may already have faded below the sensitivity of our observations. Their particles may have mixed into intergalactic space. Their magnetic fields may remain. Their energy may have become part of the thermal and magnetic environment of the cosmic web. The original radio galaxy could become difficult to recognize while its effects persist. Porphyrion is still visible to us because radio emission from its enormous structure reached instruments sensitive enough to detect it. But the universe may contain the remains of many other outflows that are harder to see. That matters when we ask whether Porphyrion is exceptional. Perhaps it is an extraordinary outlier produced by a rare combination of power, longevity, orientation, and environment. Perhaps very few black hole jets ever reach these scales. Or perhaps systems like this were more common than we realise, and most have become faint enough that finding them requires better surveys. The discovery of thousands of giant jet systems in modern low-frequency radio observations suggests that enormous outflows are not as rare as astronomers once assumed. Porphyrion pushes that idea into uncomfortable territory. If one system reached 23 million light-years, there may be others, and every one of them raises the same question. How did the jet survive? For now there is no satisfying single answer. They were powerful, they were collimated, they moved through a particular environment. Their magnetic structure mattered. Their interaction with surrounding gas shaped their evolution. Their lobes and cocoons changed the space through which later plasma travelled. Some combination of these effects allowed Porphyrion to remain recognisable over 7 megaparsecs, but the precise reason it succeeded where most jets stop far earlier is still being worked out. That uncertainty is not a gap we need to hide. It is one of the most useful things about Porphyrion. A system like this tells physicists where their explanation has to improve. Before its discovery, a 5 megaparsec ceiling looked increasingly plausible. Porphyrion moved the ceiling. Now the models have to follow. Finding something 23 million light-years long might sound as though it should be easy. After all, if you misplace something that large in your house, you would probably notice. Astronomy is less cooperative. Porphyrion had been sending radio waves across the universe for billions of years before anyone realised that several faint features in the sky belonged to one enormous system. It did not announce itself as a single bright object. The pieces were spread across a large area, the radio emission was faint, and the galaxy responsible for the entire structure appeared as a tiny source near the middle. The problem was not that Porphyrion was too small to notice. It was that it was too large, too distant, and visible in a part of the electromagnetic spectrum that human eyes cannot see. The instrument that changed this was LOFAR, the low-frequency array. The word telescope usually brings to mind a large metal tube, a dome, and someone looking through an eyepiece. LOFAR looks nothing like that. It is a network of radio antennas distributed across Europe. Instead of collecting visible light with one large mirror, many antennas detect low-frequency radio waves arriving from the sky. Computers then combine those signals so that the network can operate as a much larger observing system. There is no astronomer sitting under LOFAR with one eye pressed against a piece of glass. There are antennas, cables, clocks, computer systems, enormous amounts of data, and researchers who occasionally discover that the universe has placed something inconveniently gigantic in the middle of their survey. Low-frequency radio observations are especially useful for searching for old and extended plasma associated with radio galaxies. The energetic electrons inside radio lobes lose energy as time passes. Older regions of a radio source can become faint, particularly at higher frequencies. Low-frequency observations can remain sensitive to these aged populations of particles, making structures visible that may be difficult to recognize in other surveys. That is exactly the sort of capability you want if the universe has hidden a pair of enormous faint radio lobes across millions of light-years. LOFAR's combination of sensitivity, resolution, and wide-area surveying made it possible to begin looking for giant radio systems on a scale that earlier observations had not provided. And interestingly, Porphyrion was not the original target. Beginning around 2018, Martinoe and colleagues were using LOFAR observations to investigate the cosmic web. The cosmic web is the enormous network formed by matter on the largest scales of the universe. Galaxies and galaxy clusters are connected through filaments, with vast lower density voids lying between them. Scientists would very much like to understand the gas, particles, and magnetic fields associated with those filaments. The difficulty is that much of the cosmic web is faint, very faint. The kind of faint where astronomy stops being a matter of taking a nice photograph and becomes a matter of carefully processing huge data sets until something barely brighter than the background begins to appear. while researchers were inspecting LOFAR radio images in search of signals connected with the cosmic web, they began noticing something else. Long radio structures, pairs of extended features associated with active galaxies, giant jets. These objects were not unknown. Astronomers had studied giant radio galaxies for decades. What surprised the team was how many appeared when LOFAR looked deeply across large regions of sky. Before observations like these, giant radio sources were known but seemed unusual. Hundreds had been catalogued over many years of radio astronomy. LOFAR began revealing them by the thousands. This immediately suggested something important. Perhaps giant radio galaxies were not as rare as the older catalogues made them appear. Perhaps our instruments had simply been missing many of them. There is a useful lesson here about astronomy. The universe we know depends partly on the tools we use to look at it. Imagine surveying animals in a forest using only your ears. You would build a very good catalogue of birds, frogs, insects, and anything else that makes a noticeable sound. After years of work, you might conclude that the forest contains surprisingly few butterflies. Then someone gives you eyes. Suddenly, butterflies are everywhere. The butterflies did not appear when the new instrument arrived. The survey became capable of finding them. Low-frequency radio astronomy can produce similar changes in our understanding of the sky. A faint radio galaxy may have existed in survey data for years without being recognized as giant structure. Its lobes may be diffuse. Its jets may be interrupted. Unrelated radio sources can lie nearby. The central host may be difficult to identify. What looks like several separate blobs can turn out to be one enormous object. Once the LOFAR team realized that very large jet systems were appearing frequently, the search became more systematic. Researchers inspected radio images themselves. Machine learning tools were used to help search for giant structures. Citizen scientists were also recruited to examine radio images through LOFAR Galaxy Zoo. This combination is useful because finding enormous radio galaxies is partly a pattern recognition problem. Computers are excellent at processing huge amounts of data. Humans, meanwhile, can be surprisingly good at noticing that a complicated collection of shapes seems to belong together. Give someone a radio image containing several faint structures and they may spot an alignment that is difficult to capture with a simple set of rules. Of course, humans also have a powerful ability to see patterns that are not really there. We find faces in clouds, animals in constellations, and occasionally a person we know in a supermarket before realizing we have been staring at a coat rack. So visual identification is only the beginning. A candidate has to survive further investigation. Porphyrion attracted attention because of its enormous apparent radio structure. Avon Gast and Martin Oy identified the system, while Martin Hardcastle, working with citizen scientists in LOFAR Galaxy Zoo, independently recognized the outflow. That independent recognition was useful. Different searchers had arrived at the same strange object, but at this stage, nobody could simply measure a line across the image, declare a new record, and go home early. The radio sky is crowded. A telescope looking toward distant space does not see objects arranged neatly by distance. It sees everything projected along the same line of sight. A nearby radio galaxy can appear beside a much more distant galaxy. A bright source may have nothing to do with the faint structure next to it. Two separate radio lobes can look aligned by accident. Finding Porphyrion meant proving that its widely separated components were connected to the same central engine. Near the apparent centre, there was an extra complication. There were two radioluminous active galactic nuclei close to the region, where the enormous jet axis seemed to pass. So which galaxy was responsible? This is where higher resolution observations became important. A survey image is designed to cover a large area efficiently. It can reveal the broad structure. Once something interesting appears, astronomers can go back and examine selected regions in greater detail. LOFAR was used again at different resolutions, including extremely detailed imaging of the central area. The broad radio map showed the enormous outflow. Sharper observations helped trace the inner radio structure and determine where the overall axis passed. The likely jet line pointed through the galaxy designated J, 152932.16 plus 6 01534.4. That name is admittedly less memorable than Porphyrion. Astronomical catalogue names often sound as though somebody dropped a calculator down the stairs, but coordinates are useful, romantic names are optional. The high-resolution radio evidence helps separate the true host from another active galaxy nearby. One of the nearby sources was a quasar-hosting galaxy lying only about 19 arcseconds away on the sky. From Earth, that is a small angular separation, but the two galaxies do not sit at the same distance. Spectroscopy later showed the neighbouring quasar at a different redshift, so the apparent central region contained unrelated active galaxies projected close together from our viewpoint. This is exactly why astronomers cannot identify a host from appearance alone. The universe has depth. A flat image does not. The next step required another radio instrument, the upgraded Giant Meter Wave Radio Telescope in India, commonly called the UGMRT. Like LOFAR, the GMRT observes radio wavelengths, but the two instruments provide different capabilities and frequency coverage. Follow-up radio observations allowed the team to examine Porphyrion's central and outer structures more carefully. The researchers also used existing optical and infrared survey information, including data connected with the DESI legacy imaging surveys. Now the faint radio pieces could be compared with galaxies visible at other wavelengths. This is one of the most important habits in modern astronomy. You rarely trust one picture. A galaxy can look one way in visible light, another in infrared, another in ultraviolet, and completely different in radio wavelengths. Each part of the electromagnetic spectrum reveals different physical processes. Visible light may trace stars. Infrared observations can help reveal older stars and dust. Ultraviolet light can trace young hot stars or energetic activity. Radio observations expose synchrotron-emitting plasma and jets. Combine them, and the object becomes easier to understand. It is like investigating a house using photographs, thermal imaging, architectural plans, and the electricity meter. None tells the whole story alone. Together, they become much more useful. The candidate host of Porphyrion appeared to be a very massive galaxy. But there was still one measurement that mattered enormously: distance. Without a reliable distance, the record did not exist. A radio structure can appear large on the sky because it is genuinely gigantic, or it can appear large simply because it is nearby. Suppose you see two airplanes. One looks twice as large as the other. That does not mean the aircraft itself is twice as big. It might simply be much closer. Astronomers face that problem constantly. The apparent angular size on an image only becomes a physical size once the distance to the object is known. For Porphyrion, this meant obtaining a reliable redshift for the host galaxy. Redshift is one of astronomy's main tools for studying distant galaxies. As the universe expands, light travelling through it is stretched toward longer wavelengths. The farther away many galaxies are, the more strongly their light has been shifted. By identifying known features in a galaxy's spectrum and measuring how far those features have moved from their laboratory wavelengths, astronomers can determine its redshift. That gives them information about the cosmic epoch at which the light was emitted, and, when interpreted with a cosmological model, the galaxy's distance. The team used the W.M. Keck Observatory in Hawaii for spectroscopy of the host. Keck's large telescope collected enough light from this extremely distant galaxy to examine spectral features and establish that Porphyrion lies about 7.5 billion light-years from Earth. That changed everything. The enormous radio structure on the image was not a relatively nearby system spread broadly across the sky. It was extremely distant. And if something that far away still appeared that extended, then its true physical dimensions had to be extraordinary. When the distance and radio geometry were combined, the full system measured about 7 megaparsecs, roughly 23 million light-years. The faint patches in a LOFAR image had become the largest confirmed black hole jet system known. There is something satisfying about how undramatic that transformation was. Porphyrion did not suddenly explode in the sky. Nobody saw a flash. No alarm sounded in an observatory. A group of scientists looked at radio survey data. They noticed an unusual pattern. Other people independently noticed it too. Then more observations were made. Different instruments were brought in. Candidate host galaxies were checked. Spectra were measured. Distances were calculated. The geometry was examined. And slowly, a collection of faint radio features became a 23 million light-year object. That is how many astronomical discoveries actually happen. Not as one grand moment, but as a series of increasingly difficult attempts to prove yourself wrong. The first question is, could this be something interesting? The next question is, what else could explain it? Maybe the northern radio feature is unrelated. Maybe the southern one belongs to another galaxy. Maybe the central host has been misidentified. Maybe its distance is wrong. Maybe the apparent alignment is coincidental. Maybe one of the components is actually a separate radio source. A good discovery has to survive those possibilities. Porphyrion did. The final radio structure contains a northern lobe and jet, a central core, a southern jet with an inner hotspot, and a more distant southern hotspot associated with backflow. Those features form a connected physical picture. They are not simply two random radio clouds with a galaxy between them. The morphology shows the behavior expected from a black hole-driven outflow. The higher resolution central observations connect the axis to the host. The spectrum gives the host distance. The radio data reveal the extended plasma. Together, the evidence produces the system we now call Porphyrion. LOFAR was essential because the outer structures are exactly the kind of faint, extended radio emission that a low-frequency survey is good at finding. Its 2-meter sky survey, usually shortened to LOTSS, maps large areas of the northern sky at frequencies around 120 to 168 MHz. To a radio astronomer, that is a useful observing band. To everyone else, it's probably enough to know that these wavelengths are far longer than visible light and allow LOFAR to detect sources the night sky keeps entirely hidden from our eyes. The survey also produces a remarkable quantity of information. Millions of radio sources appear in LOFAR catalogues. Most are nowhere near the size of Porphyrion. Many are compact galaxies, active nuclei, star-forming galaxies, and other radio-emitting objects. Some are parts of extended systems. Separating all of them is a data problem as much as an observing problem. This is why wide surveys have changed the way astronomy works. A century ago, an astronomer might spend a night examining a limited number of objects. Modern surveys can produce catalogues containing millions. The difficulty has shifted. We can collect more of the sky than any individual researcher could inspect carefully. Now, we have to work out how to search it. That is where machine learning and citizen science become particularly useful. An algorithm can flag candidate structures. A volunteer can inspect an image. A professional astronomer can evaluate the promising cases. Higher resolution observations can test them. A discovery that began with antennas scattered across Europe can end with a telescope on a Hawaiian mountaintop, measuring a galaxy billions of light-years away. There is a pleasant amount of international cooperation required to discover one very long object. Porphyrion even demonstrates how different kinds of observers can contribute. Its discovery was not solely the product of one automated pipeline. Human inspection mattered. Citizen scientists played a role in independently finding the outflow. Specialists then followed the evidence using several instruments and forms of analysis. There are problems for which the human eye remains remarkably useful. A complicated radio galaxy can have curves, gaps, lobes, cores, unrelated foreground sources, and faint emission at different scales. Recognizing that these features form one physical system sometimes requires a kind of visual reasoning that does not begin with a neat equation. You look at the image and think, those might belong together. then science begins the much less romantic job of checking whether you're right. The name Porphyrion came later. Eyvind Gast, one of its co-discoverers, suggested the name after Porphyrion, one of the giants of Greek mythology. The earlier record holder, Alcyonius, had also been named after a mythological giant. At this point, astronomers discovering very large radio galaxies appear to have established a theme. Fortunately, Greek mythology contains a reasonable supply of giants. They may need them. Because Porphyrion was not the only surprise coming from the LOFAR search. The larger survey effort revealed more than 10,000 giant jet systems, vastly expanding the known population. The exact samples and selection methods continue to be refined, but the broad result is clear. The radio sky contains far more giant black hole outflows than astronomers once realized. That changes the question. Originally, researchers could ask why giant radio galaxies were so rare. Now they have to consider whether many were simply difficult to detect. A large object can be faint. An old object can have diffuse radio emission spread over a huge area. A distant system can become harder to associate with its host. Some sources may lie partly outside surveyed regions. Others may be oriented in ways that reduce their apparent length. And there may be relic systems whose central engines have already quieted while the old lobes continue fading into the intergalactic medium. Our catalogues are therefore not complete inventories of what exists. They are inventories of what our instruments and search methods have managed to recognize. LOFAR improved that recognition dramatically. Even then, the search that produced Porphyrion had covered only part of the sky when the object was reported. That leaves a rather obvious possibility. There may be larger systems, not because Porphyrion is unimpressive, but because record holders in astronomy often survive only until the next survey becomes good enough. Alcyonius was announced as the largest known radio galaxy in 2022. 2 years later, Porphyrion pushed the record much farther. Perhaps 23 million light-years is close to the practical limit for a black hole jet system. Perhaps not. Maybe there is a 25 million light-year source hiding between catalogue entries. Maybe 30. Maybe something even larger has already been observed, but not recognized because its lobes are faint, disconnected in appearance, or associated with a host whose distance has not yet been measured. A radio map does not label these things for us. There is no line drawn from one lobe to the other saying same black hole. Astronomers have to build that connection themselves. The more sensitive the survey, the stranger some of those connections may become. Porphyrion also reminds us that discovery and understanding are different stages. LOFAR showed that the giant existed. Follow-up observations identified its host. Keck established how distant it was. Radiomorphology showed how the components fit together. Models helped estimate how the jets may have grown. But none of those steps fully explains why a black hole was able to produce a coherent outflow on such an extreme scale. Finding Porphyrion created new questions faster than it answered old ones. That is generally a good sign in science. The other surprise came from its distance. If Porphyrion had been a nearby system, its size would still have broken the record. Instead, astronomers found it billions of light-years away. Porphyrion is about 7.5 billion light-years away. When we look at it, we are not seeing Porphyrion as it is now. We are seeing it as it was roughly 7.5 billion years ago. That sounds simple enough because we've all heard that looking into space means looking into the past. But with Porphyrion, the distance is large enough that the phrase stops being a nice astronomy fact and becomes essential to understanding the object. The radio waves detected by LOFAR began travelling toward the part of the universe that would eventually contain us billions of years before anyone on Earth built a radio telescope. They travelled while our solar system continued orbiting the Milky Way. They travelled while Earth changed. Continents moved. Species appeared and disappeared. Our ancestors evolved. Civilizations rose. People invented writing, mathematics, telescopes, radio antennas, computers, and eventually enough astronomy terminology to make falling asleep significantly easier. Only then did those ancient radio waves reach instruments on Earth. So the Porphyrion we observe is an old version of Porphyrion. Very old. At the time we're seeing it, the universe was roughly 6.3 billion years old. Today, the universe is about 13.8 billion years old. That means we are looking back to an era when the universe was less than half its current age. This does not take us anywhere near the beginning of the universe. Stars and galaxies had already existed for billions of years. Large galaxies had formed. Supermassive black holes were active. The cosmic web was well established. Galaxy clusters were developing. There was already plenty going on. Still, the universe at that time was not the same place we live in today. It was younger, it was denser, galaxies were generally closer together. The cosmic web was more compact. Star formation across the universe was much more active than it is now, and active supermassive black holes were more common. Porphyrion therefore existed during a period when the universe was a busier environment in several important ways. To understand why, we need to talk about expansion. The universe has been expanding for billions of years. This does not mean galaxies are simply flying outward from one central location into empty space. There is no known center of cosmic expansion from which everything is racing away. Instead, on very large scales, the distances between widely separated regions of the universe increase as space itself expands. The common comparison is dots drawn on the surface of an inflating balloon. As the balloon grows, the dots become farther apart, even though none of them needs to be the center of the surface. The universe is not literally the surface of a balloon, and the analogy becomes troublesome if we push it too far, but it helps with one basic idea. A smaller, earlier universe had matter packed more closely together. Run cosmic expansion backward, and large-scale distances shrink. Galaxies that are widely separated today were closer together in the past. The filaments of the cosmic web were closer together too, and the average density of matter was higher. This matters enormously for Porphyrion. We have already asked how two jets could remain organised across 23 million light-years. Now imagine trying to do that when the surrounding universe was much denser than it is today. The researchers who reported Porphyrion estimated that jets of this kind existed during an epoch when the universe was around 7 to 15 times denser than the present universe, depending on the part of the system's history being considered. For a jet trying to grow to enormous size, that is not obviously helpful. A jet does not travel through perfect emptiness. It encounters intergalactic gas. It pushes material aside. It drives shocks. Its edges can become unstable. It loses energy. The surrounding medium can influence its shape and its speed. A less dense universe might seem like the easier environment for building a very large radio structure. There is less material to encounter. The jet can travel farther before being slowed or disrupted. That is one reason astronomers have tended to associate the most enormous radio systems with the more recent universe. Given enough cosmic time, expansion makes intergalactic environments thinner. A powerful black hole jet operating later in cosmic history might therefore have an easier path. Porphyrion complicates that picture. It became enormous when the universe was much younger. Not a little enormous. Not unusually large for its time. It became the largest black hole jet system we have ever confirmed, ancient or modern. That forces us to reconsider what the early universe allowed. Of course, average density does not tell us what the jet encountered at every point along its route. The universe is not filled evenly with matter. Some regions are dense, others are extremely empty. Galaxies gather in groups, clusters, and filaments. Between those structures lie voids. Even in an overall denser universe, a jet launched in a favourable direction could leave a relatively dense region and expand into thinner surroundings. Porphyrion appears to have had exactly that kind of opportunity. Its host galaxy is associated with a filament of the cosmic web. A cosmic filament is an enormous structure containing galaxies, gas, and dark matter. It can stretch for many millions of light years. Galaxies often form and grow along these filaments because matter naturally gathers there under gravity. The filaments then meet in denser regions containing galaxy groups and clusters. Between them are much emptier voids. If Porphyrion's jets were launched away from the filament and toward lower density regions, they could have encountered progressively easier conditions as they travelled outward. That does not fully explain their size, but it may be part of the answer. Imagine trying to move through a busy railway station. Near the centre, progress is slow. People are everywhere. You need to change direction repeatedly. Then you reach an empty platform late at night. Suddenly there is space. A jet leaving a cosmic filament may experience a much more dramatic version of that change in density. And because Porphyrion's jets were so long, they could extend far beyond the immediate neighbourhood of their host galaxy. They crossed a distance equal to a large fraction of the scale of a typical cosmic void at the time. The discovery paper estimates that the 7 megaparsec radio structure spans about 2/3 of the radius of a typical void from that epoch. That is a very different picture from a jet remaining inside one galaxy. We're talking about an outflow launched near one supermassive black hole, extending across a meaningful portion of the large-scale structure of the universe. This is why the age of Porphyrion matters. A 23 million light-year jet system in the nearby universe would already be extraordinary. A 23 million light-year jet system, when the universe was less than half its current age, raises a larger question. How common were giant jets back then? There are reasons to suspect the answer might be more common than we once thought. Supermassive black holes were often more active during earlier periods of cosmic history. Galaxies contained larger supplies of gas. Interactions and mergers between galaxies were more common because galaxies were closer together. Large amounts of material could be driven toward galactic centres. And when a supermassive black hole receives enough fuel, the central region can become an active galactic nucleus. Porphyrion's own central source is especially interesting, because observations indicate that it was in a radiatively efficient mode of accretion. This type of active black hole was more common in the younger universe. That means Porphyrion may not represent some completely unique kind of engine that existed once and then disappeared. The basic class of active nucleus capable of powering it was relatively common during that period. What seems exceptional is what the jets managed to become. That distinction changes the possibilities. Suppose Porphyrion required a type of black hole so unusual that only one existed in 1 trillion galaxies. Then finding another system of comparable size might be very unlikely. But if ordinary members of a fairly common population of active black holes could occasionally produce jets this large, then the young universe might have contained many enormous outflows. Most would not necessarily still be easy to detect. Radio structures age. Their energetic electrons lose energy. Lobes expand. The central black hole may stop producing jets. Over billions of years, the radio emission can fade. Structures can mix with surrounding intergalactic gas. So the fact that we can identify Porphyrion does not mean every ancient system like it remains visible. There may have been a large population whose obvious radio signatures are now too faint for current surveys. This becomes especially important because jets do not need to remain visible forever to leave permanent consequences. Suppose an ancient black hole sends magnetized plasma several million light years into intergalactic space. Eventually the jet shuts down. The bright radio emission fades. The lobe expands and mixes with its surroundings. Billions of years later, an astronomer may no longer recognize the original radio galaxy. But the energy deposited into that environment did not magically return to the black hole. The particles went somewhere. The magnetic fields went somewhere. The surrounding gas was heated and moved. Shocks passed through it. The intergalactic medium remembers the event even after the radio source becomes difficult to see. This is where Porphyrion begins affecting our ideas about cosmic history rather than simply our list of very large objects. The universe contains magnetic fields on enormous scales. Galaxies have magnetic fields. Galaxy clusters have magnetic fields. Evidence suggests that even the thin matter associated with the cosmic web may contain extremely weak magnetism. Where all of those large-scale magnetic fields originated remains an important question. Small seed fields may have been created in the early universe, or through later astrophysical processes. Those seed fields could then be amplified. Galaxies, stars, supernovae, and black hole activity can all contribute to moving and strengthening magnetic fields. Giant black hole jets are particularly interesting because they can transport magnetized plasma far away from galaxies. Porphyrion demonstrates that this transport can occur across several megaparsecs. That means one active galaxy can carry magnetic material into regions of intergalactic space very distant from its host. And if many giant radio galaxies existed in the young universe, their combined influence could have been much larger than previously assumed. Picture the cosmic web during the time of Porphyrion. The filaments are closer together than they are today. Galaxies are more densely packed. Active black holes are common. Now imagine giant jets repeatedly extending from those galaxies. One system reaches a few million light years. Another stretches through a different filament. Another grows into a nearby low-density region. The jets eventually fade, but their particles and magnetic fields remain behind. Over billions of years, cosmic expansion stretches the large-scale structure while galaxies continue forming and evolving inside it. Even if the original jets vanish from view, they may have contributed material and magnetism to regions that later became much more widely separated. Porphyrion suggests that black holes might have reached farther into this younger, more compact cosmic web than astronomers had assumed. This is an important consequence of doing the same physical action at different cosmic times. Imagine painting dots on a rubber sheet. Place several dots close together, then stretch the sheet. The dots end up much farther apart. If something could influence several neighbouring regions before the stretching occurred, those affected regions would later occupy a much larger volume. A giant jet in the early universe therefore has an advantage in terms of eventual reach. It acts while the cosmic web is compact. Expansion later increases the distance between the regions it influenced. Porphyrion's 23 million light-year span was already enormous at the time we observe it. The material affected by systems like it would then continue participating in billions of years of cosmic evolution. This does not mean Porphyrion itself caused galaxies across the modern universe to form. That would be a much stronger claim than the evidence supports, but it shows that black hole activity had the physical ability to influence matter well outside individual galaxies at relatively early times, and that makes black holes more important players in the history of the intergalactic medium. Usually we think of supermassive black holes as objects belonging to galaxies. The Milky Way has one, Andromeda has one. Massive galaxies generally seem to contain them. They sit in the centre and participate in the evolution of their host. Porphyrion encourages a different view. A supermassive black hole can live inside a galaxy, while its influence extends well beyond the galaxy. The address may be galactic. The consequences can become cosmological. That is particularly striking when we remember how small the central region is. The host galaxy itself is only a tiny part of the 23 million light-year system. The active nucleus is smaller still. The region close to the black hole where the jets are launched is almost absurdly tiny compared with the distance those jets eventually cover. Yet that central process can redistribute energy on a scale approaching the structures connecting many galaxies. And all of this happened billions of years ago. That last fact can become confusing because astronomy uses distance and time almost interchangeably when discussing very distant objects. When we say Porphyrion is around 7.5 billion light-years away, we are giving a useful description of how long its light has travelled to reach us. But cosmic distance is more complicated than simply multiplying the light travel time by the speed of light and imagining the galaxy sitting at a fixed location. The universe expanded while the radiation travelled. Porphyrion's host and the Milky Way are part of a changing cosmic geometry. The present-day distance to the region where that galaxy exists now is therefore not the same as the simple, 7.5 billion light-year light travel distance. For our purposes, the important fact is the look back. The signal gives us access to the galaxy as it existed billions of years ago. Astronomers identify that epoch through redshift. Porphyrion's host has a measured redshift of roughly 0.9. Redshift tells us that the light has been stretched as the universe expanded during its journey. Imagine a wave drawn on an elastic strip. Stretch the strip and the distance between wave crests increases. Something similar happens to light travelling through expanding space. Its wavelength becomes longer. Visible light shifts toward the red end of the spectrum, which is where the term redshift comes from. The same effect applies beyond visible wavelengths too. By measuring how much recognizable spectral features have shifted, astronomers can estimate how much the universe has expanded since the light was emitted. Then a cosmological model connects that redshift with the age of the universe, distance, and other properties. So when Keck spectroscopy helped establish the distance to Porphyrion's host, the astronomers were doing more than locating the galaxy. They were placing Porphyrion on the timeline of cosmic history. That changed the scientific meaning of the discovery. Before the distance was known, there was an enormous apparent radio structure. After the redshift was established, astronomers knew that this structure existed when the universe was only around 6.3 billion years old. The record was ancient, and this is not what researchers had expected from the known population of giant radio galaxies. Previously, the larger systems had seemed largely associated with the relatively nearby, more recent universe. That encouraged a reasonable assumption that there might be something about late cosmic conditions that allowed radio jets to become extremely large. Perhaps the lower density helped. Perhaps black holes could remain active in jet-producing states for longer. Perhaps the environments of older massive galaxies were more favourable. Then Porphyrion appeared in the distant universe. Suddenly, enormous jets were not merely a late universe phenomenon. A black hole had managed to build the largest known example during an epoch when the universe was younger and denser. That means our earlier picture may have been influenced heavily by what we were able to detect. Nearby giant radio galaxies are easier to study. Their radio structures appear brighter. Host galaxies are easier to identify. Distances are easier to obtain. An ancient giant radio galaxy has several disadvantages. It is farther away. Its emission reaches us after billions of years of travel. Surface brightness becomes a serious observational challenge. The radio lobes may be faint. The host can be difficult to distinguish from unrelated galaxies along the same line of sight. So perhaps distant giant radio galaxies were not absent. Perhaps we were simply better at finding the nearby ones. Lofar begins changing that, and Porphyrion may be an early example of a population that is only now becoming visible to us. This is why one discovery can change a statistical argument. Imagine studying birds in a forest and seeing only small species for years. You conclude that large birds are rare. Then someone builds a better observation platform and discovers one enormous bird in a region you previously could not examine properly. One bird does not tell you the complete population, but it tells you that large birds can live there. Your earlier absence of evidence becomes much less convincing. Porphyrion does the same thing for extreme jet systems in the distant universe. It proves that black hole jets could reach roughly 7 megaparsecs during an epoch when conditions were very different from today. How frequently that happened is still uncertain. The next generation of surveys will help answer it. For now, we can at least say that the universe was capable of producing extraordinary radio structures much earlier than the previous record holders had suggested. There is another consequence of looking so far into the past. We cannot know what Porphyrion is doing today. There is sometimes a temptation to imagine pointing a telescope at a distant galaxy and seeing what is currently happening there. We cannot. The telescope receives the information available to us now, but that information left the source billions of years ago. Whatever happened to Porphyrion after the era we are observing has not yet reached us. The jets may have stopped. The black hole may have entered a quieter phase, The host may have changed significantly. It may have merged with another galaxy. Its surrounding cosmic structure will certainly have evolved as the universe expanded. There may no longer be anything resembling the radio system shown in the LOFAR image, or some descendant of that activity may remain. We will not see those later stages until their radiation has had time to reach our region of the universe. In that sense, astronomy does not give us a live map. It gives us a map made from different times. The moon appears as it was about a second ago, the sun about 8 minutes ago, nearby stars years ago, Andromeda millions of years ago, Porphyrion billions of years ago. Look farther in any direction, and you automatically move backward through cosmic history. A deep astronomical image can therefore contain nearby objects from the relatively recent past and distant galaxies, from a much younger universe in the same field. They look as though they occupy one picture. They belong to different eras. Porphyrion occupies an era particularly useful for understanding the evolution of galaxies and black holes. By around 6 billion years after the Big Bang, the universe was mature enough to contain massive galaxies and enormous supermassive black holes, but still young enough that many galaxies had abundant gas, and active nuclei were far more common than they are today. The most intense period of cosmic star formation had already peaked earlier, but the universe remained much more active than the nearby cosmos. Porphyrion's host existed within this changing population. Its central black hole had access to enough fuel to operate in a radiatively efficient state, while also producing powerful jets. Those jets then escaped beyond the galaxy and travelled across an environment shaped by the denser cosmic web. Each part of that situation tells us something different. The galaxy tells us that massive systems were already well developed. The active nucleus tells us that its black hole was feeding efficiently. The jets tell us that the central engine could channel enormous amounts of energy outward. Their length tells us the outflow could remain effective over millions of light years. And their age tells us all of this was possible long before the present-day universe took shape. Put those facts together, and Porphyrion stops looking like an isolated curiosity. It becomes evidence about what black holes were capable of doing during a major period of cosmic evolution. That is why astronomers are interested in finding more systems at similar or greater distances. One object tells us something is possible. A population tells us whether it was important. Suppose future surveys find hundreds of Porphyrion-like systems from the same era. Suppose instead Porphyrion remains almost unique. Then researchers will want to understand what unusual combination of black hole power, lifetime, orientation, and environment allowed this one system to grow so far beyond the others. Either answer is useful. The universe has already done the experiment. Astronomers now have to find enough of the results, and Porphyrion gives them a reason to keep looking. Once Porphyrion's jets had escaped their host galaxy, their journey was no longer only about how far they could travel. They were changing the space they travelled through. That may sound strange because intergalactic space is often described as empty. Between galaxies there are no forests, oceans, buildings, or obvious clouds. In many regions, matter is so thinly spread that a cubic meter can contain fewer particles than some of the best vacuum chambers we can build on Earth. But empty is a dangerous word in astronomy. Intergalactic space contains gas. It contains charged particles. It contains magnetic fields. Dark matter contributes most of the gravitating matter that shapes the large-scale structure, while ordinary matter, the material made of protons, neutrons, and electrons, occupies the same enormous network in much thinner forms. And gravity has not arranged all of this material evenly. Over billions of years, matter gathered into the structure we call the cosmic web. If we could step far enough away from the observable universe and somehow make its large-scale matter distribution visible, galaxies would not appear as dots sprinkled randomly through space. They would trace a network. Long filaments connect denser knots containing groups and clusters of galaxies. Broad sheets of matter run between some regions. Enormous voids occupy the spaces in between. The appearance resembles a web, although there is no spider involved, which is probably for the best considering the dimensions. Galaxies like Porphyrion's host live inside this structure. Their gas supply, their neighbours, their movement and their evolution are influenced by it. The cosmic web is not merely scenery behind galaxies. It is the environment in which galaxies grow. Gas flows along filaments. Galaxies gather there. Clusters develop where several dense structures meet. And between the galaxies lies material that is difficult to observe directly because it is often thin, hot, and faint. Now place Porphyrion inside this network. Near the centre is one massive galaxy. Inside that galaxy is an active supermassive black hole. From the region around that black hole came two jets. Those jets left the galaxy, passed beyond its halo, and continued into intergalactic space for millions of light years. By the time the system reached roughly 7 megaparsecs from end to end, the jets were operating on scales comparable with significant parts of the cosmic web itself. And a jet travelling through intergalactic gas does not simply move past it, it pushes. At the leading regions of a powerful radio source, the jet transfers momentum into the surrounding medium. Gas ahead of the advancing structure can be compressed. Shock waves can form. Energy carried from the central black hole is converted into heat, particle motion, magnetic energy, and the growing radio lobes. So although the space is thin, the interaction is physical. Imagine pushing your hand through water. The water moves around it. Waves form. Energy is transferred from your arm into the liquid. Now imagine something moving through air. The effects are weaker because air is less dense, but a fast object can still produce pressure changes and shocks. A jet entering intergalactic space faces matter vastly thinner than air, but the jet is also enormously energetic and continues interacting with that material across distances measured in millions of light years. The result is that a black hole can deposit energy very far from the galaxy containing it. This is one form of what astronomers call feedback. The word feedback sounds harmless enough. In daily life, feedback might mean someone telling you that your presentation could use a smaller font, or that perhaps 8 slides about office chairs were unnecessary. Black hole feedback is more energetic. An active galactic nucleus releases radiation, winds, and jets. Those outputs interact with gas around the galaxy. They can heat it. They can move it. They can make it harder for gas to cool. They can change how easily future stars form. For years, astronomers have studied this process because galaxies and their central black holes appear to evolve together. The black hole is tiny compared with the galaxy, yet when it becomes active it can release enough energy to influence gas on galactic scales. Porphyrion expands the area we need to consider. Its jets did not stop at the edge of the host. They reached millions of light years beyond it. That means some of the energy generated near one black hole was delivered into regions far outside the galaxy, whose gas originally helped feed that black hole. The relationship stops being purely local. One galaxy can affect space associated with the wider cosmic web. How much it affects that space depends on several things. Jet power matters, lifetime matters, the density of the environment matters, the direction matters, the shape and pressure of the radio lobes matter, and the way the jet mixes with surrounding gas matters. Porphyrion does not give us a complete measurement of every one of those effects. What it does provide is proof that an individual system can reach extraordinary distances. That gives researchers a physical mechanism capable of transporting energy far from galaxies. Consider the radio lobes. As jets feed them, the lobes expand. They contain energetic particles and magnetic fields, and their internal pressure can push against the surrounding intergalactic medium. Expansion requires work. The lobe moves surrounding material outward. It changes pressures. It can create shocks. Some of its energy eventually becomes heat in the surrounding gas. The central black hole may be millions of light years away, but the energy being deposited originated in the activity around that black hole. This makes giant radio galaxies unusual delivery systems. They take energy from a compact region and distribute it across volumes of space that the host galaxy itself could never occupy. A normal galaxy influences its neighbourhood through gravity, radiation, winds, supernovae, and interactions with nearby galaxies. An extreme jet allows the central engine to reach far beyond that ordinary neighbourhood. Porphyrion did it when the cosmic web was more compact than it is today. That makes the possible effect larger in another sense. Because the filaments and other structures of the early universe were closer together, an enormous outflow could cross a greater fraction of the distance between important parts of the web. Porphyrion's 7 megaparsec extent was estimated to equal roughly 2/3 of the radius of a typical cosmic void at the time. That does not mean its jets filled an entire void. A radio jet is much narrower than the enormous 3-dimensional volume of a void, but it tells us that the length scale is comparable. A structure generated by one black hole was approaching the dimensions of features created by the large-scale distribution of matter itself. That is where astronomers become especially interested in magnetism. Magnetic fields are found throughout astronomy. Earth has a magnetic field. The Sun has one. Stars have them. The Milky Way contains a large-scale magnetic field. Other galaxies do too. Galaxy clusters contain magnetized plasma. Observations also suggest that magnetic fields extend into much thinner regions associated with the cosmic web. The difficult question is where all that magnetism came from. Magnetic fields can be amplified once they exist. Moving electrically conducting plasma can stretch and strengthen them. Turbulence can amplify them. Rotating galaxies can organize them. Stars, supernovae, and active galactic nuclei can carry magnetized material outward. But before you amplify a magnetic field, you need some initial field to amplify. Astronomers therefore discuss different possible origins. Some magnetic fields may trace extremely weak seed fields created very early in cosmic history. Others may have been introduced or strengthened later by astrophysical objects such as galaxies and black holes. The final magnetism we observe may involve several processes operating together. Porphyrion does not settle that debate. It does, however, demonstrate that active black holes have impressive range. A jet is made of plasma moving through magnetic fields. The magnetic field is not a decorative addition around the jet. It is deeply involved in how the plasma behaves. Magnetic fields can help launch and collimate jets near the black hole. They continue travelling with the plasma as the jet expands. When that plasma reaches a lobe millions of light years away, the lobe is magnetized too. Then the lobe expands. It interacts with the intergalactic medium. Eventually its contents may mix with the surrounding material. In that way, a black hole can transport magnetic fields from the environment of a galaxy into much larger volumes of space. Now imagine this happening not once, but repeatedly. Porphyrion is the largest confirmed example, but LOFAR has revealed thousands of giant radio systems. Most are smaller, many are much smaller. But they do not have to equal Porphyrion individually for their combined effect to matter. If giant jets were common during periods when active black holes were more abundant, then large numbers of galaxies may have injected magnetized plasma into the cosmic web. One radio galaxy affects one region, another affects a different region. Their lobes grow, their jets shut down, their radio emission fades, the magnetized material remains and mixes. Billions of years pass. Cosmic expansion stretches the distances between structures. Later galaxies and clusters grow inside environments that may already have been affected by previous generations of active black holes. That is one possible route through which black hole jets could contribute to large-scale cosmic magnetism. It remains a possibility being investigated, rather than an established explanation for all the magnetism in the universe. That distinction matters. Finding Porphyrion proves that a jet can reach these distances. It does not prove that Porphyrion magnetized every region inside a sphere 23 million light-years wide. the jets occupy a much smaller volume than such a sphere. Nor does it prove that black hole jets are the original source of every magnetic field we observe. Scientists still have to determine how much magnetic energy giant jets carry, how efficiently it escapes the lobes, how the fields mix with surrounding plasma, how long those fields survive, and how frequently similar systems existed throughout cosmic history. But before Porphyrion, one could reasonably wonder whether jets were able to carry their influence across enough distance to become important on cosmic web scales. Now we know at least one pair did, and probably not only one. Magnetism is not the only thing being transported. The jets also carry energetic particles. Some of these particles are electrons, the particles responsible for much of the synchrotron radio emission that allowed LOFAR to see Porphyrion. But jets can also contain atomic nuclei. Some particles can be accelerated to extremely high energies in jets, shocks, and hotspots. When energetic charged particles travel through space, we often refer to them broadly as cosmic rays. The name makes them sound like a form of radiation similar to light, but most cosmic rays are particles rather than electromagnetic waves. Many are protons. Some are heavier atomic nuclei. Their origins vary. Supernova remnants are important accelerators within galaxies. Active galactic nuclei and their jets are leading candidates for producing some of the highest energy cosmic rays in the universe. Porphyrion therefore represents another possible way to inject energetic particles into intergalactic space. Again, the word possible is useful. We do not have a jar labelled particles from Porphyrion sitting in a laboratory. The system is billions of light years away, and charged particles are deflected by magnetic fields during their journeys. Tracing individual cosmic rays back to one distant radio galaxy is extremely difficult, but the physical environments in powerful jets and hotspots are capable of accelerating particles, and Porphyrion shows how far a jet can carry energetic plasma away from the central galaxy. Heavy elements enter the discussion as well. Hydrogen and helium dominated ordinary matter in the early universe. Elements such as carbon, oxygen, silicon, and iron were produced later inside stars and in stellar explosions. Galaxies therefore become chemically enriched over time. Gas that has been processed by generations of stars contains heavier elements. Active galaxies can move some enriched material outward through winds and other outflows, and radio jets can interact with and entrain material from their surroundings. The researchers studying giant jets are interested in their ability to distribute atomic nuclei and enriched matter beyond galaxies. This does not mean Porphyrion manufactured iron inside the jet. The black hole is not running a chemical factory with a particularly aggressive shipping department. The elements are produced by stars and stellar processes. The role of galactic outflows is transportation. Once material escapes or is carried far from a galaxy, it can enrich the intergalactic medium. Over cosmic time, this helps explain why gas outside galaxies is not made only of pristine hydrogen and helium. Then there is heat. A jet carries enormous mechanical energy. When it drives shocks into surrounding gas, some of that energy becomes thermal energy. The gas heats. When a radio lobe expands, it performs work on its environment. Turbulent motions can eventually dissipate into heat. Particles transferring energy to surrounding material contribute too. This matters because the temperature of intergalactic gas affects what happens next. Gas must often cool before gravity can gather it efficiently into dense structures where stars can form. Heat it enough, and cooling becomes harder. That can reduce the supply of cold gas available to galaxies. In galaxy clusters, feedback from central black holes is already known to be important, because jets can inject enough energy to help prevent hot gas from cooling too quickly. Porphyrion raises the question of whether similar effects, distributed over much greater distances, could influence gas outside traditional cluster environments. We should not imagine one Porphyrion jet switching off star formation across half the universe. The surrounding gas is too extensive, and the detailed impact depends on where the energy goes. But locally, along the path of the jets and around their lobes, the outflow can change the physical state of the material it encounters. If many giant radio systems occupied the early cosmic web, those local effects could add together over time. This is the point where population becomes more important than one record holder. A single rainstorm changes one landscape. Thousands of storms shape a climate. One jet tells us what is possible. Thousands tell us what may have been common enough to matter. And Lofer's discovery of large numbers of giant radio galaxies has made that second question much harder to ignore. There is also the matter of redistribution. The cosmic web contains most of the ordinary matter in the universe, but much of it is difficult to detect. Some baryonic matter lies in hot, diffuse gas around and between galaxies. Feedback from galaxies and black holes can push that matter outward from dense regions. Computer simulations of galaxy formation have shown that feedback processes can affect how baryons are distributed well beyond the visible parts of galaxies. Jets provide a particularly directional form of that feedback. Instead of heating everything equally around the host, they carve out specific routes. They can create cavities. They can move material aside. They can inflate lobes into surrounding gas. Over time, those lobes rise, expand, mix, and fade. The final result may look nothing like the bright radio structure that produced it. This is important because astronomy often observes the current state of a system and tries to reconstruct events that are no longer visible. Suppose an ancient giant radio galaxy switched off several billion years ago. The narrow jets would disappear. The most energetic electrons would lose energy. The radio lobes would become fainter. Eventually the structure might be extremely difficult to detect, but the gas it heated would still have been heated. Material it displaced would still have been moved. Magnetic fields it introduced could still remain in some form. The active phase ends. The environmental consequences continue. Porphyrion is valuable partly because we have caught an ancient example, while enough radio emission remains visible for us to reconstruct the outflow. We can see the route, we can identify the host, we can measure the scale, and that gives scientists a physical example to use when asking what invisible remnants other jets may have left throughout the universe. There is another consequence worth considering. Galaxies do not evolve independently. Gas moves through the cosmic web toward them. A galaxy's ability to form new stars depends partly on receiving and retaining gas. If a powerful jet heats or displaces intergalactic gas near another forming galaxy, it could change that galaxy's future supply. If it compresses gas in some locations, the result could be different. Feedback is rarely a simple matter of turning star formation off. The outcome depends on pressure, temperature, density, timing, and the structure of the surrounding material. Researchers therefore speak carefully about Porphyrion's possible influence on galaxy formation. Its discovery shows that black hole activity can extend much farther than previously demonstrated. That makes interactions with environments beyond the host galaxy more plausible. Determining exactly how strong those interactions were requires simulations and additional observations. The scale, however, is no longer hypothetical. 23 million light-years exist in the data. That alone changes what models have to allow. And because Porphyrion lived in a younger universe, its timing could be particularly important. Back then, cosmic filaments were packed closer together. A jet of a given length could reach across a larger fraction of the surrounding large-scale structure than the same jet would today. Later, expansion increased those separations, so an early population of giant jets could potentially have distributed energy and magnetism through regions that cosmic expansion later carried farther apart. This gives ancient black hole activity a way of leaving effects across a larger present-day volume than the original jet length might suggest. Imagine adding a drop of ink to a piece of elastic material before stretching it. The ink affects one compact region at first. Stretch the material afterward, and the marked region becomes more widely distributed. The universe is obviously more complicated than an elastic sheet. An intergalactic plasma does not remain fixed to simple marks, but the basic timing issue matters. Act early, when structures are closer together, and later expansion changes the scale of the affected environment. This is one reason Porphyrion's age and size cannot be separated. Its enormous reach would be interesting at any epoch. Its enormous reach in the younger universe makes its possible cosmological influence much more significant. It also gives astronomers another route for investigating magnetic fields. If giant radio galaxies spread magnetism through the cosmic web, then observations of radio emission, Faraday rotation, polarized sources and diffuse structures may eventually help trace that history. Magnetic fields affect the polarization of radio waves passing through magnetized plasma. With enough background radio sources and sufficiently sensitive instruments, astronomers can use these effects to probe otherwise nearly invisible material. Future radio observatories will dramatically increase the number and quality of such measurements. That may help answer whether regions influenced by giant jets show different magnetic properties from regions that were not. The question is difficult because the cosmic web is faint, the fields are weak, and many processes may contribute. But Porphyrion has provided an unusually large laboratory. A laboratory 7 megaparsecs long is admittedly inconvenient if you are hoping to keep it on a desk. Still, the principle is the same. Observe a system, measure its properties, compare it with models, look for consequences, find more examples. That final step is essential. One Porphyrion cannot tell us how common 7 megaparsec jets were. It cannot establish how much magnetism the entire population injected into intergalactic space. It cannot tell us whether most giant radio sources lived in similar environments. For those questions, astronomers need a census. Fortunately, LOFA has already shown that there are far more giant radio galaxies than the old catalogue suggested. And Porphyrion is not the first object to move the upper limit. Before it, another giant had already surprised the same community. Alcyone stretched roughly 5 megaparsecs and briefly held the record as the largest known radio galaxy. Before Alcyone, other systems had held it. Each discovery pushed the known boundary a little farther. Then Porphyrion moved it from roughly 5 megaparsecs to 7. That pattern suggests that the current record may tell us as much about the sensitivity of our surveys as it does about the actual maximum size nature can build. If giant jets shape the cosmic web, the most important objects may not necessarily be the largest one. A population of moderately smaller jets could collectively deposit far more energy than one record holder. But the record holders show what the population is physically capable of doing. They establish the extreme end. They tell us that the influence of one active galaxy can cross millions of light years of intergalactic space, and once a limit moves from 5 megaparsecs to 7, there is an obvious question sitting quietly in the radio sky. Was Porphyrion the exceptional endpoint? Or is it simply the largest member we have managed to recognize so far? The search has been much messier than that. For decades, enormous radio galaxies were known, but finding them was difficult. Their lobes could be faint. Their jets could be broken into pieces on a radio map. The galaxy responsible for the whole structure might sit between features separated by millions of light years. And unless the host galaxy had a reliable distance measurement, an impressive object on the sky could not easily be converted into an impressive physical size, so records change slowly. One system would appear to be the largest. A better measurement might alter its size. Another object would be discovered. Then someone would reanalyze an older survey and realize that an even larger structure had been sitting in the data for years. Astronomy is full of discoveries that were technically observed long before anyone understood what they were looking at. Giant radio galaxies are especially good at this. Their size can actually make them harder to recognize. A compact radio source is conveniently located in one place. A very large radio galaxy may be spread across such a broad region that its different components can initially look unrelated. One lobe appears here, another is far away. Several smaller radio sources sit between them. There are galaxies everywhere in the optical image. Some of those galaxies are nearby. Some are billions of light years farther away. The astronomer has to decide which pieces belong to the same physical system. It is less like finding a large elephant in a field, and more like finding one ear in Scotland, another ear in France, and then trying to prove that somewhere between them there really is an elephant. This is one reason the history of giant radio galaxies is also a history of better surveys. As radio telescopes improved, astronomers became sensitive to fainter and more extended structures. As computers improved, larger areas of sky could be processed. As optical and infrared surveys became more complete, possible host galaxies could be identified more reliably, and as redshift catalogues grew, apparent radio sizes could be converted into real physical lengths for larger numbers of systems. The record holders therefore tell us two things at once. They tell us what black hole jets can do. They also tell us what our instruments have become capable of noticing. Before Porphyrion, one of the most important names in this story was Alcyonius. Alcyonius was reported in 2022 by a team that included several of the researchers who would later work on Porphyrion. Like Porphyrion, it was named after a giant from Greek mythology. Astronomers apparently decided that if black holes were going to produce structures several megaparsecs long, ordinary catalogue numbers were no longer emotionally adequate. Alcyonius had a projected radio size of about 5 megaparsecs. That corresponds to roughly 16 million light-years. At the time, it was described as the largest known structure of galactic origin, and one of the most interesting things about Alcyonius was that the galaxy responsible for it did not appear especially extraordinary. Its radio power was not at the extreme end of the giant radio galaxy population. Its host galaxy was not the most massive. Its central black hole was not obviously some uniquely monstrous object. It seemed, in several respects, surprisingly ordinary for a galaxy that had produced the largest known radio structure. That result immediately made the search more interesting. If the largest radio galaxy required the most massive black hole, the highest jet power, and the most unusual host galaxy, then astronomers could build a simple story. Exceptional engine, exceptional result. Alcyonius did not cooperate. Its enormous scale suggested that environment, lifetime, geometry, and the long-term history of the jets could matter just as much as raw power. Perhaps a jet does not need to be the strongest. Perhaps it needs to remain active for a long time. Perhaps it needs to travel in a favourable direction. Perhaps the surrounding intergalactic medium has to be thin enough. Perhaps several conditions that are individually ordinary occasionally combine to create something enormous. Then Porphyrion arrived. Its radio structure extended roughly 7 megaparsecs, around 23 million light-years. The old 5 megaparsec region that had once looked suspiciously close to a natural upper limit was suddenly no longer a limit at all. Porphyrion exceeded it by about 2 megaparsecs. That extra distance alone is millions of light-years, and because the system existed in a much younger, denser universe, it challenged the idea that only late cosmic conditions could allow jets to grow to extreme sizes. For a while, the progression looked beautifully simple. Alcyonius at about 5 megaparsecs, Porphyrion at about 7. Record broken, case closed. Astronomy rarely leaves a case closed. The same large LOFAR surveys that helped reveal Porphyrion were producing catalogues containing thousands upon thousands of giant radio galaxies. A 2024 population study using the LOFAR 2-meter sky survey combined machine learning searches, crowdsourced candidates, and visual confirmation to bring the known population of giant radio galaxies to well above 11,000. That is a remarkable change from the earlier era when only a few hundred giants were known, and once your sample grows from hundreds to more than 10,000, the extreme end of the population becomes much more interesting. Imagine rolling a pair of dice 10 times. You may not see anything unusual. Roll them 10,000 times, and rare combinations become inevitable. The same statistical principle applies to astronomical populations. If extremely large radio galaxies are rare, a small survey may never include one. Search a much larger volume of the universe with better sensitivity, and rare giants begin appearing. That seems to be happening now. In fact, the record associated with Porphyrion has already become more complicated. Later, LOTSS catalogue work includes a radio system associated with TXS 0033+252, also catalogued under a rather less bedtime-friendly LOFAR designation. Its reported projected radio extent is close to 8 megaparsecs, roughly 26 million light-years. That would make it larger in projected radio extent than Porphyrion's roughly 7 megaparsecs. So depending on the specific catalogue, measurement and terminology being used, Porphyrion should now be described carefully. It was the record-setting black hole jet system reported in 2024 and remains one of the most extraordinary radio structures known, but the search has already produced a candidate with an even larger reported projected extent. And honestly, this is exactly what we should expect. A scientific record is not a medal permanently attached to an object. It is a statement about the best observations available at a particular time. Change the observations and the statement may change. This is especially important for giant radio galaxies because measuring their size is not as simple as putting a ruler against a photograph. First, astronomers have to decide which radio emission belongs to the source. Where does the lobe end? Is a faint patch part of the system, or an unrelated background source? Does the jet continue through a low surface brightness region that the current observation barely detects? Are there older plasma structures beyond the obvious hotspot? Different imaging depths and frequencies can reveal different boundaries. Then there is the host distance. A small change in redshift interpretation can change the physical size. Cosmological parameters enter the conversion. The angular extent has to be measured. Projection matters. The jets may not lie exactly across the plane of the sky. So when one system is reported as 7.0 megaparsecs and another as 8.0, the comparison is scientifically meaningful, but it's not the same as measuring two wooden boards in a workshop. The uncertainties and definitions matter. This is why astronomers are often more interested in the population than in arguing endlessly about which object deserves a trophy. Porphyrion matters because it demonstrates that black hole-driven outflows can reach around 7 megaparsecs in the distant universe. Alcyonius matters because it demonstrated that a fairly ordinary host could produce a 5 megaparsec system. TXS 0033+252 matters because catalogue measurements suggest that the extreme tail may extend farther still. Together, they tell us that enormous jet systems occupy a range rather than ending neatly at one record holder. The next question is how far that range continues. There could be a physical ceiling. Jets cannot grow forever. The central black hole has to remain capable of supplying energy. The jet has to remain collimated. Instabilities have time to develop. The radio-emitting electrons lose energy. The surrounding environment pushes back. Cosmic expansion changes large-scale conditions. Eventually, something should limit the growth. But the location of that limit is no longer obvious. 5 megaparsecs once looked plausible. Porphyrion crossed 7. Catalogued candidates are approaching 8. Maybe 10 megaparsecs is possible. Maybe 15 is not. Maybe a rare combination of jet power, long activity, low environmental density, and favourable geometry allows a system to grow far beyond anything we have yet seen. Or perhaps the known examples are already close to what nature can manage. The way to find out is not to guess from one object, it is to search more sky. That process has accelerated dramatically. The LOFAR 2-meter sky survey was designed to map the northern radio sky at low frequencies with enough sensitivity and resolution to detect enormous numbers of radio sources. Its second major data release covered only part of the northern sky and still contained millions of sources. By the third data release in 2026, the survey images covered about 88% of the northern sky. The catalogue contained roughly 13.7 million radio sources. 13.7 million. Even if only a tiny fraction turn out to be giant radio galaxies, That is still an extraordinary hunting ground. Of course, nobody's going to examine 13 million sources one by one over breakfast. This is where modern astronomy increasingly becomes a partnership between telescopes, software, machine learning, citizen scientists, and professional researchers. A computer can search for extended radio components. Algorithms can try to associate separated features. Optical catalogues can provide possible host galaxies. Photometric and spectroscopic redshifts can estimate distances. Machine learning systems can rank promising giant candidates. Humans can inspect difficult cases. Then the most interesting systems can receive dedicated follow-up observations. Porphyrion itself illustrates why all of these stages matter. Simply detecting radio emission was not enough. Its pieces had to be connected. The correct central galaxy had to be identified. Its redshift had to be established. Higher resolution radio observations were required. Only then did the physical scale become convincing. A future record holder will probably require the same kind of detective work. And there may be a peculiar bias in what we find. The largest radio galaxies are not necessarily the easiest ones to detect. As a radio lobe expands, its energy is spread over a larger volume. The surface brightness can fall. Older electrons lose energy. The outer structure becomes diffuse. A very large, very old radio galaxy may therefore become faint enough that a smaller, younger system is easier to see. That means the true record holder could be one of the least visually impressive objects in a shallow radio image. It may not appear as a pair of brilliant lobes. It could be an enormous haze. Its central black hole may already have quieted down. The host may look completely ordinary. Only low-frequency observations with excellent sensitivity to extended emission might reveal the full structure. There is also the problem of orientation. Suppose a radio system is physically 10 megaparsecs long, but points partly toward Earth. Its projected size on the sky could look much smaller. It would not enter a catalogue as a 10 megaparsec giant unless astronomers could reconstruct the viewing geometry accurately. The longest projected systems are therefore biased toward jets lying relatively close to the plane of the sky. Some physically enormous systems may be hiding in shorter apparent forms simply because of the direction they happen to point. And then there is the southern sky. LAFAR has transformed surveys of the northern sky, but other radio facilities are mapping different regions and frequencies. ASCAP in Australia has already discovered new giant radio galaxies. Meerkat in South Africa provides exceptional sensitivity and image quality. The Square Kilometre Array, with major components in Australia and South Africa, is expected to push radio astronomy much further as its capabilities grow. Future surveys will detect fainter sources, resolve complex structures, and observe enormous areas with a consistency that earlier generations could not approach. Every improvement creates another chance to move the upper limit. There may even be giant radio systems whose lobes overlap with unrelated sources so thoroughly that current algorithms fail to connect them. A future machine learning model may discover them simply because it becomes better at recognizing morphology. This is an unusual kind of exploration. Astronomers not traveling physically farther into space. They are improving the way existing signals are separated from noise and interpreted. The radio waves may already be sitting in stored observations. The object may already have a catalogue entry. Its host may already have a measured redshift. What is missing could simply be the realization that several pieces belong together. The next record holder may therefore be discovered tomorrow using data collected years ago. That possibility makes the search for giants different from searching for something like a new comet. A comet moves. A transient explosion happens. A giant radio galaxy can sit in the same direction for the entire history of human astronomy. We simply need to become good enough at seeing it. Records also become less important once the population grows. At first, it is natural to focus on the largest object. Alcyonius gets attention because it reaches 5 megaparsecs. Porphyrion reaches 7. TXS 003 3 plus 2, 5-2 approaches 8. But after thousands of giants have been catalogued, another question becomes more powerful. Why do their sizes follow the distribution they do? How common are 1 megaparsec systems? How rare are 3 megaparsec systems? How rapidly does the population fall off beyond 5? Does the distribution change with cosmic time? Do the largest giants prefer particular environments? Do they avoid dense galaxy clusters? Are they more likely to grow along directions leading away from cosmic filaments? Does black hole accretion mode affect the maximum size? Does host mass matter? Does jet power matter less than lifetime? These questions cannot be answered by one famous object. They require statistics, and modern surveys finally provide enough giants to begin doing that properly. The 2024 LOFAR population study found that giant radio galaxies are more common than older samples had suggested. That does not mean they are ordinary. A structure more than 0.7 megaparsecs long is still an extreme product of black hole activity, but earlier estimates were affected strongly by selection. We were missing many giants because surveys were not sensitive enough, not wide enough, or not designed to connect large diffuse components. Once those observational biases are modelled, the universe appears to contain more giant radio systems than the older catalogues implied. This also changes our interpretation of Porphyrion. The most interesting question may not be why one bizarre object became so large. It may be how often the universe creates the conditions required for systems in this extreme tale. A record holder attracts attention. A distribution explains physics. If 10,000 giants exist in current catalogues, then each one contributes a small piece of information about black hole activity, jet lifetime, environment, and cosmic history. Porphyrion sits near the far end of that distribution. It tells us that the tail reaches at least several megaparsecs farther than astronomers once thought, and whatever object eventually becomes the undisputed largest will probably do the same thing again. It will not make Porphyrion unimportant. Alcyonius did not become unimportant when Porphyrion surpassed it. Scientific objects do not lose their value when they lose a record. Alcyonius remains a remarkable example of how an apparently ordinary host can generate an extraordinary structure. Porphyrion remains crucial because its size, redshift, morphology, and early cosmic epoch demonstrated that coherent jets can reach cosmological distances under conditions previously thought highly unfavourable. A larger object adds another piece. It does not erase the old one. Perhaps that is the most useful way to think about these giants, not as contestants standing on a podium, but as experiments performed by nature. One black hole operated under one set of conditions, another lived in a different environment. Their jets grew for different lengths of time. They had different powers, orientations, magnetic structures, and histories. Astronomers find the remains and compare the outcomes. The larger the catalogue becomes, the better we can work backward from those outcomes to the physics that produced them. Somewhere in the new LOFAR maps, there may already be another structure that will force those models to stretch again. Perhaps its lobes are separated by 30 million light years. Perhaps its central galaxy has not yet been identified. Perhaps one half is obvious, and the other is buried in diffuse emission. Perhaps it has already been seen by a citizen scientist who marked it as unusual and moved on to the next image. We do not know, and for tonight that uncertainty is useful. Because after spending all this time asking which jet is longest, how black holes launch them, how they survive, and what they do to intergalactic space, the record itself begins to feel like only one small part of the story. Whether Porphyrion remains first, second, or eventually 10th on some future list, the important fact stays the same. A galaxy billions of light years away once contained a black hole whose activity reached across a distance that would take light tens of millions of years to cross. We found it because radio waves survived the journey to Earth, and now that the surveys are becoming deeper, wider, and more complete, we are beginning to see that Porphyrion was never alone. So after all of that, we can return to the small galaxy in the middle. Not small in any ordinary sense, of course. Porphyrion's host contains an enormous population of stars. It is a massive galaxy with a supermassive black hole in its centre, living billions of light years away. But place that galaxy beside the radio structure produced by its active nucleus, and it becomes a tiny feature. The stars occupy one region. The jets continue far beyond them. The lobes extend farther still. By the time the entire system is drawn at once, the galaxy responsible for everything can look like little more than a mark near the midpoint. That is probably the strangest part of Porphyrion. Not simply that something in the universe is 23 million light-years long. The universe contains much larger structures. Galaxy filaments extend for hundreds of millions of light-years. The cosmic web covers scales so large that 23 million begins sounding strangely manageable. What makes Porphyrion different is the source. This enormous radio structure can be traced back to activity around one black hole in one galaxy. One central engine influenced a region far larger than the galaxy containing it. That is what we have been following from the beginning. We started with the name, Porphyrion, a mythological giant attached to a real structure in the distant universe. Then we had to make an important correction to the obvious interpretation. The host galaxy itself is not 23 million light-years across. Its stars do not stretch over that distance. The enormous measurement belongs to the radio jets and lobes powered by the central active galactic nucleus. That distinction matters because it tells us what kind of giant we are dealing with. This is not a galaxy that somehow grew until it occupied a significant fraction of a cosmic void. It is a galaxy whose black hole produced an outflow capable of reaching those scales. The galaxy is the source. The radio structure is the consequence. And for human eyes, almost all of that consequence is invisible. If we could look directly toward Porphyrion without instruments, there would be no enormous beam cutting across the sky. The radio emission lies outside the wavelengths our eyes detect. Even with optical telescopes, the host galaxy would not reveal the full extent of the system. It took radio astronomy to make the structure visible. Lafar detected the faint emission. Higher resolution observations helped connect the pieces. Other telescopes helped identify the host. Spectroscopy established the distance. Only after those measurements were combined did the scale become clear. Around 7 megaparsecs, approximately 23 million light-years, a number large enough that our usual comparisons quickly stop helping. We tried anyway. We crossed the solar system. We went to nearby stars. We stretched across the Milky Way. We lined up galaxy-sized distances. We compared Porphyrion with the gap between the Milky Way and Andromeda. And after all of that, the object was still inconveniently large. Perhaps the simplest comparison is still the most useful. Light travelling at about 300,000 kilometers per second would require roughly 23 million years to cross a distance equal to the system's full observed span. There is no faster messenger available to us. 23 million years. That is how large the radio structure became. Then we moved inward, toward the centre, because size alone does not explain anything. At the heart of the host galaxy, matter was falling toward a supermassive black hole. It formed an accretion flow. The plasma heated. Magnetic fields became important. Energy from infalling matter, and potentially from the rotation of the black hole itself, became available to power narrow relativistic outflows. Two jets emerged in opposite directions. The black hole did not spit matter back out from inside its event horizon. Nothing escaped after crossing that boundary. The jets were produced by the energetic environment outside it. That small distinction prevents a very common misunderstanding. Black holes can power enormous outward flows without anything escaping from inside the black hole. The energy conversion happens before the matter disappears beyond the horizon. And once the jets were launched, they faced another problem. They had to survive. They crossed the environment of the host galaxy. They entered thinner gas farther out. They interacted with the intergalactic medium. They carried plasma and magnetic fields. They developed lobes and hotspots. They They deposited energy. They encountered conditions that could bend, slow, or destabilize the flow. Yet Porphyrion remained coherent over millions of light years. We do not know exactly how it managed that. That uncertainty is still part of the science. Power probably mattered. Magnetic fields probably mattered. The environment mattered. Its direction relative to the cosmic filament around its host may have given the jets access to increasingly low-density regions. Its lifetime mattered. But there is no single established explanation that turns 7 megaparsecs into an obvious result. Porphyrion exists first. The models have to catch up. Then came another surprise. The system is ancient. The radiation reaching Earth shows Porphyrion as it existed roughly 7.5 billion years ago, when the universe was around 6.3 billion years old. The universe was denser then. The large-scale cosmic environment was more compact. Active black holes were more common. Galaxies contained more available gas. Conditions were different from the relatively mature universe around us today. And yet one black hole managed to build an outflow larger than the extreme radio structures that had previously been found mostly at later cosmic times. That makes Porphyrion useful as a historical record, not historical in the human sense. Nobody wrote down what the black hole was doing. There was no observer standing beside the host galaxy with a notebook. The record is stored in radiation. Radio waves left the system. They travelled through expanding space. Billions of years later, antennas on Earth detected them. When astronomers analyse that signal, they recover information about a period of cosmic history that ended long before our planet developed anything capable of asking questions about it. That is one of the strange advantages astronomy has over other historical sciences. The past is still arriving. Every night, old information reaches Earth. Light from the moon is a little over a second old. Sunlight is about 8 minutes old. Nearby starlight may be years old. The light from Andromeda is millions of years old. Porphyrion's signal is billions of years old. The farther we look, the older the message. There is no universal live feed of the cosmos. The sky is a collection of different pasts. Porphyrion belongs to one of the older ones we have discussed tonight, and because it existed in that younger universe, its enormous reach may have mattered in ways we are only beginning to investigate. The jets did not travel through meaningless emptiness. They travelled through the cosmic web. Intergalactic gas surrounded them. Large-scale filaments connected galaxies. Lower density regions lay between those structures. As Porphyrion advanced, it transported energy away from its host. It carried charged particles. It carried magnetic fields. It drove shocks. Its lobes expanded. It altered the material directly in its path. We do not know the exact long-term effect of this one system. It would be too strong to say Porphyrion magnetized the entire cosmic web or determined how galaxies formed across some enormous region. The evidence does not support that. But it demonstrates the required reach. A black hole jet can transport its influence over several megaparsecs. Once we know that is possible, the population becomes important. If many giant jets existed in the younger universe, their combined effects may have spread energy and magnetism through a substantial amount of intergalactic space. The radio structures eventually fade. The particles and fields do not simply vanish because the object drops below our detection threshold. They mix with their surroundings. The central engine can shut down, while the environment continues carrying evidence of what happened. This means the present-day cosmic web may contain traces of ancient black hole activity whose original radio galaxies can no longer be reconstructed clearly. Porphyrion is valuable because one of those ancient events remained visible enough to find. Then we met Alcyoneus, a 5 megaparsec giant that had once held the size record. Its host appeared surprisingly ordinary in several respects. That told astronomers that exceptional size did not require the most obviously exceptional galaxy. Porphyrion then pushed beyond the 5 megaparsec range. More recent catalogue work has pushed the search farther again, with systems such as TXS, 003, 3+2, 5.2 reported at a projected radio extent near 8 megaparsecs, and that brings us to an important correction to the way records sound in science. When Porphyrion was reported, calling it the largest known black hole jet system was accurate. A record means largest known at the time under the measurements available. It does not mean largest that has ever existed. It does not mean nature cannot make a bigger one, and it does not mean another survey will not change the ranking. That is already happening. The better our radio maps become, the more giant systems appear. LOFA surveys have transformed the known population from a relatively small collection into many thousands of giants. Its newest large data releases contain millions upon millions of radio sources. Somewhere among them may be structures whose components have not yet been connected. The next enormous jet system does not need to be created in the future. It may have formed billions of years ago. We simply have not recognized it yet. That gives the whole story a slightly different ending from the one we might have expected. We began with the largest. We end with uncertainty about what largest even means. Not because the measurements are useless, but because the frontier is moving. 5 megaparsecs looked extraordinary. 7 changed the limit. 8 may push it again. Better surveys will test whether 10 is possible. At some point, physics should impose practical limits. Jets cannot remain active forever. They cannot stay perfectly organized over unlimited distances. The surrounding universe affects them. The central engine evolves. The particles lose energy. The source eventually fades. There must be some region of parameter space where even the most favorable black hole jet can grow no farther. We have not yet established where that boundary is, and perhaps that is more interesting than a permanent record holder would be. A known maximum gives you a number. An unknown maximum gives you a research problem. Porphyrion provided an excellent one. How can relativistic jets remain coherent for so long? How common were giant radio systems in the early universe? Which environments allow them to grow? How long do their central engines remain active? How effectively do radio lobes magnetize intergalactic gas? How much energy do giant jets deposit into the cosmic web? How many ancient systems have already faded beyond recognition? And how large can one black hole-driven structure ultimately become? Those questions are still open. Some will be addressed with LOFAR, some with other radio telescopes, some with optical and infrared spectroscopy, some with computer simulations. The Square Kilometre Array and other next-generation facilities will search the radio sky with sensitivity and scale that should reveal populations we currently see only incompletely. Astronomers will build larger catalogues. Algorithms will learn to connect radio components more effectively. Citizen scientists will probably continue finding objects that automated systems overlook, and every so often, someone will notice 2 faint patches separated by an unreasonable amount of sky and ask whether they might belong together. That is how this field moves forward, not by assuming that the current picture is complete, by looking for the parts that do not fit. Porphyrion did not fit. A 7 megaparsec jet pair was not expected. Its early cosmic epoch was inconvenient. Its radiatively efficient central engine was interesting. Its scale challenged proposed growth limits, and its possible influence on intergalactic magnetism made the object relevant far beyond the simple question of size. That is why it will remain important even if dozens of larger radio systems are discovered. Scientific discoveries do not become worthless when their records disappear. Pluto did not cease being interesting when its classification changed. Mountains do not become geologically unimportant because a taller mountain exists somewhere else. Alcyonius did not become ordinary when Porphyrion was found. Porphyrion will not become ordinary when something longer replaces it. The useful part is what each object teaches us. Porphyrion teaches us that one active galaxy can produce a structure on a scale approaching the architecture of the cosmic web. That is a remarkable result regardless of ranking, and after spending so much time with distances measured in megaparsecs and powers expressed with 39 zeros, it may help to come back to Earth for a moment. Where are you listening from now? Perhaps the same place you were when we began. Maybe the room is darker. Maybe the screen brightness has quietly become offensive. Perhaps you've heard every word. Perhaps you fell asleep somewhere around synchrotron radiation and returned just in time for the ending, which is honestly an excellent use of a sleep video. Outside your room, Earth continues rotating. The moon moves along its orbit. The planets continue around the sun. The solar system moves through the Milky Way. Our galaxy travels within its local group, while the universe expands on much larger scales. None of those motions require us to notice them, and far beyond our galaxy, old radio waves are still crossing space. Some come from active black holes, some from supernova remnants, some from galaxies forming stars, some may come from enormous radio structures that nobody has identified yet. The antennas are listening, the data are accumulating, the next Porphyrion may already be there. For tonight, though, there is no need to search for it yourself. You do not need to remember 7 megaparsecs. You do not need to remember catalogue names. You certainly do not need to remember J152932.16 plus 6, 01534.4, unless you have an unusually competitive astronomy quiz scheduled tomorrow morning. It is enough to keep the basic idea. A supermassive black hole in a distant galaxy became active. Matter spiraled inward. Magnetic fields and relativistic plasma produced 2 powerful jets. Those jets escaped the galaxy. They travelled through intergalactic space. They remained organised over millions of light years. They inflated enormous radio structures. Their radiation crossed the universe. LOFAR detected it. Astronomers connected the pieces. And an event that began around one black hole billions of years ago became something we can sit quietly on Earth and learn about tonight. There is an enormous difference in scale between those two places. One is a central region around a black hole. The other is a radio structure millions of light years long. And then there is us, on a planet so small compared with either that the comparison barely works. Yet size does not determine what can be understood. We do not need to travel across Porphyrion to measure it. We do not need to approach its black hole to study its activity. We collect the information that reaches us and work backward. A radio wave arrives at an antenna. A spectrum contains shifted lines. A faint galaxy appears in an image. A computer joins observations taken at different times and different wavelengths. From those pieces, we reconstruct something larger than any distance a human being could ever cross in a lifetime. That may be the nicest thing about astronomy to take with you as the lights go out. The universe does not need to be nearby for us to learn from it. It only needs to leave evidence. Porphyrion left quite a lot. So as you settle a little more comfortably, you can let the numbers go. 23 million light years can become simply very far. 7.5 billion years can become very long ago. The black hole can remain where it is. The radio jets can continue across the old universe captured in our observations, and here, in a much smaller place, there is nothing left to measure tonight. If you found this journey calming or interesting, you can leave a like and subscribe to Science for Sleep. It helps these quiet science explorations reach other people who enjoy ending the day with something slightly larger than tomorrow's schedule. And perhaps let me know where you were listening from. Somewhere under the same sky, radio waves from distant galaxies are passing overhead, whether we notice them or not. Most will never meet a human eye. Some will reach an antenna. A few will reveal something nobody knew was there. For now, the surveys can keep listening. The black holes can keep their secrets a little longer, and you can get some sleep.